Some notes are posted from last time, including sideways, but you'll be able to print it out and it'll be okay. And I think you can even, with PDF, can you rotate? I always forget how to do that. Control shift something or other, arrow key or anyway. So including those notes that I developed for you last time that show you how to or remind us of the big picture. So you probably find that useful to review the overall story. We're going to get back into the trees today again for some things. And then toward the end of the day, after we finish the unit on hierarchical modeling, which will occupy much of our day, we're going to start on part 5, which is something that will occupy us for several weeks running, thinking about Bayesian model specification from first principles, and that will also have another big picture aspect to it. So that's new, and I have written a chapter recently in a book. Adrian Smith is one of the great Bayesians of the 20th and early 21st centuries. He's retired recently, and so Paul Damian and one of Adrian's students and a few other of his students organized a conference in his honor, and I gave a talk there and wrote a chapter in the book that came out from this. And so again, on the topic of Bayesian model specification, I think you'll find this to be quite readable, and I'll be showing you some of the examples from it as we go along. The videos from week 5 are now posted, so we're up to date on that. And there's a bunch of new things down here under code. No new data sets. We're going to be working with the aspirin meta-analysis case study data in WinBugs. Also, I'll show you how to do the sampling in R. And then we'll talk about a new hierarchical model in what's called the teacher expectancy case study. And then we'll spend a fair amount of time with a random effects Poisson regression model that introduces the idea of latent variables or random effects and mixing over them to do a better job of describing heterogeneity in the data than ordinary parametric models do. And time permitting, we'll also look at this Berkeley proportional bicycle traffic case study, which is more complicated than the other ones. I might save that for later in the final couple weeks about applications. So the main stuff that's new here, Chris Severs from eBay has done 2 things very useful for us. He's figured out how to run WinBugs under Mac OS X if you want to do that. In fact, that could easily be the path of least resistance for Mac users in this course, because I'll be showing you principally WinBugs examples from here on out with occasional RJAGs examples. And so rather than having to convert my WinBugs example into an RJAGs and run it that way on your Mac machine, you can learn from Chris how to get things so that WinBugs runs under OS X. He's figured out how to do it using a product called Crossover, and the actual details, I guess, Chris, people can write to you for those details. Okay, or if you want, you can write them down and send them to me, and I'll post more elaborate details here on the webpage so that people can do a step-by-step. That'd be great. Chris has also done something very valuable for us, which is to figure out how to run RJAGs in parallel processing mode, which of course greatly speeds up the whole MCMC experience. And I'll show you his example today, in fact, just in a few minutes. With 4 CPUs instead of 1, you get speed-ups on the order of 3 to 3.5. There's a little bit of overhead in actually doing the parallel stuff, so you don't get a factor 4 speed-up, but you get a speed-up on the order of 3 to 3.5. And we'll see how to do that today. I'm going to show an example of what happens when you're interested in parameters in a model that are what people call non-identifiable. So there's issues of identifiability in some models that arise both from a frequentist and a Bayesian sense. And I'll show an example of how that sort of thing can arise and how it plays out in the Bayesian paradigm. And then Later on, we're going to have occasion to look at quality of care, measurement of quality of care in health and medicine, example in which non-Bayesian ways of analyzing the data, in particular using unbiased estimation, which used to be a very favorite frequentist technique, and still many people like it, in which this setting in which frequentist unbiased estimation produces a ridiculous result. And so I have some handwritten notes on what's going on, and then R code for generating the data, and so we'll look at the story in WinBugs. So that's the stuff that's new. And I'm going to go ahead and run the parallel RJAGS code now and show you how it goes. So I've downloaded it here. There's a slight improvement to it that he and I just added a few moments ago, but I'll post the improvement to the web page probably over lunch. So what I gather what Chris did is to get some pointers from a website. We've talked about Andrew Gelman before. He's the co-author of one of the books I recommended to you. And he is a guy who's interested not only in Bayesian theory and Bayesian methods, but also in Bayesian applications, but also helping people to actually do this stuff by giving ample advice on how to run code and so on. So he has a web page you could go to about parallel JAGs, and Chris started there and then specialized it to our NB10 example, and I think added a few whistles of his own. So I'm going to need to start an R session. And the first thing I'm going to do, let's see if that's as big as it can get. Like the instructions here say, the first thing I'm going to do is to change directory to the location where I have previously stored the model file. Remember, that was the first step in the previous story. What I'm doing now is to build upon the NB10 RJAGS example in that file I showed you last week called How to MCMC Sample with RJAGS that's on the course webpage. So if you go back to the course webpage, we have this thing, How to MCMC Sample with RJAGS, and you'll see that the first thing we did was to change directory to the place that we wanted to store the model file. So that's our first instruction right here. Inside R, change directory to that location. So I'll go up here under File and choose Change Directory and catch local disk C. For me is where things are, and I go down to Short Courses and eBay Google 2013 and the place called NB10-JAGS. That's the folder in which I had this particular file. Then we're going to need 3 packages from CRAN, the Comprehensive R Archive Network. And so I gave you instructions on how to install packages in that file, How to MCMC Sample with RJAGS. So if you haven't installed them already, you need to do that now. Here I've already done the installing, and so a reminder how you do it is you go up to Packages and hit the Install Packages button, and it asks you where do you want to go for a mirror, and I usually use one or the other of the USA mirrors. And then you have all these packages, and we want to use the one called Do Parallel, for example. So you just page down here until you find Do Parallel, and you would then go ahead and double left click on Do Parallel, and it would be installed, and then in order to actually use it, you have to load it, and you can do that either with the load package pull down or with the library command, and that's interesting. Oh, no worries from that. So here I run the library command to bring all 3 of these in because I've already previously installed them, and so they should come in now with a little bit of mumbling as usual about how the packages were built under possibly different versions of R than the one we have here. Looks like I started with, should say somewhere, does it say it right there? Yes, 2.15.1, and these were all created under 2.15.2. So probably to make those warnings go away, I can just update R, but no problems. Then he points out that for OS 10 and Linux, you can optionally use this register do parallel command, but I'm going to show you how to do it under Windows. You put a number inside there that tells the R code how many processors you want to use. So here I'm going to give you an example with 4 processors. and I run this stuff here. The very first time I did it, I got a message from Windows saying, you're about to mess with something that's basic. Do you really want to do that? And I said yes, and everything was fine. And from that point on, running it later, I got no such message anymore. And so now he creates a function to generate the initial values and random seeds for each model, which is similar to what I showed you before, except he has extra details about how to get random number seeds up and running. So I'll go ahead and run that function. And then this is exactly the stuff we used last time, exactly the same code for bringing in the data. So I'll bring that guy in as well. And now he's written a helper function to combine multiple MCMC lists into a single one. So we'll define that function as well. And then we're about to run the NB10 example with a burn-in of 1,000 and a monitoring run of 100,000. And when we're using 4 chains, we're going to give 25,000 iterations to each chain after its own burn-in. Then later on, we'll compare that with a single-threaded run in which we ask for only one processor and use all 100,000 iterations there, and we'll see what kind of time results. So I define the variable iters, and then I run this system time command. And what's cool about the system time command in R is that you can put all sorts of things you want to do inside system time, open parenthesis, close parenthesis, so open parenthesis right there, close parenthesis down there. You can put all sorts of stuff in there that you want to do, and when you're done, it will it'll do all that stuff and give you a breakdown of how long it took to do it. So let's go ahead and read this stuff in, and I'll go ahead and then both run it and print how long it took to run. So let's have a go. And what it's now doing is the burn-in. Let's see, if it's trying to talk, I should unbuffer the output, but I think it's not actually trying to talk to me. So each processor is now doing its burn-in of 1,000 and its monitoring of 25,000, and then we'll combine that into one big MCMC data set at the end automatically with the software and get an equivalent to having done a burn-in of 1,000 followed by 100,000 monitoring iterations from a single processor, but at approximately 3 to 3.5 times the speed up. So here the elapsed time was about 30.9 seconds on the clock, and that's, as you'll see in a minute, much faster than if we'd asked for single threading. So let's go ahead and run the single threaded code. And now again I change the iterations to 100,000 and I run the code for one processor at a time. And now you remember this is like what we did last week, in which after the burn-in, after initializing the model, which is relatively quick, and the burn-in of 1,000, so those steps are the same in both the 4 processor and 1 processor versions, it now takes an unpleasantly long period of time to get its 100,000 iterations from the single processor. So this will take another 30 to 45 seconds probably before this finishes. While we're waiting for it, does anybody have any questions or comments, either for Chris or for me?
So presumably it's made 4 output files similar to.
That's right.
It's combined all into one MCM. No, I'm talking about the console. Oh, right. We didn't see any console output.
Yeah, it's running. It's doing this cluster business where it's running on a cluster.
Right.
And so it just doesn't show any output.
Yeah, it doesn't think it has a console, I guess. So
if you run it in like OSX or
this is really going to make it possible to use MCMC in settings in which it was infeasible to do so. For example, at eBay they have a large Hadoop cluster. I bet there's something like that here as well at Google. and in many other places in the valley and around. And what we're able to do then is fit Bayesian nonparametric models, which take an enormously long time to run and require an enormously large number of iterations to actually explore the parameter space thoroughly. I have been trying to figure out for several years how to get Bayesian nonparametrics to work on big data sets, and the idea of spreading the MCMC out across 8,000 nodes or whatever you've got available to you is going to make it possible to do Bayesian nonparametrics with 1 million data points. It comes completely into focus. And it's not something it is a topic that for full efficiency, it's a topic that's at the research frontier. We're hiring a new assistant professor at Santa Cruz right now, and one of the 5 shortlist candidates who came to give a job talk, that was the entire content of her talk, was about how to parallelize MCMC in a fully efficient way for Bayesian nonparametrics using Dirichlet process mixture modeling, which I'll show you later on. And so she regards it as essentially still completely at the research frontier. But we can use the tools I'm showing you right here. If we have things like 8,000 processors in a Hadoop cluster, we can overwhelm the problem with raw computing power rather than having to rely upon very cutting edge results that aren't even published yet, which is what she was talking about. So look, it took 106 seconds of elapsed time to do the single thread. And if I divide that by the 30.9 seconds that it took to do the 4 thread, I get a speed up on the order of about 3.4 on my machine. So now let's look at the results. Of course, this has all just been getting results one way or another. I showed you how to use homegrown files in my example called How to MCMC Sample with RJAGs. I wrote homegrown functions for graphically and numerically summarizing the results of the MCMC, but you can simply use a bunch of functions that are already built into the CODA routines that were loaded as part of this written by Martin Plummer. So instead of going through my homegrown code, let's go ahead and just use the plot function. jags.parsesamples is an object of type mcmc.list, I think, and so you can, when you've passed that object to plot figures out what kind of object it is and does the right thing. And so that's interesting. When I'm running on my machine without plugging it into this device here, which forces the resolution to be smaller, I had no difficulty running this code before, but now in the plotting command, it fails to work on this occasion because the figure margins are too large for the actual space that's allowed under this smaller resolution. So I'll have to work that out for you during the break. But we certainly can do a summary of this guy and get the numerical summaries that come out naturally from what Martin Plummer looks at. And so he's producing values that are like what I was showing you. We get posterior means and standard deviations, and we get Monte Carlo standard errors by 2 different methods. I showed you the time series standard error using that formula involving the first order autocorrelation. There's another way to get Monte Carlo standard errors that actually produces numbers that are only relevant if the chain is behaving like an IID white noise chain. So notice how the thing called naive standard error for y.new, which always in the way we're doing the MCMC produces output that's like an IID white noise chain. The naive standard error is the same as the time series standard error, but with all the other ones, it's substantially larger when you take account of the autocorrelation. So when the series, you should always look in the column called time series standard error, and the difference between those two, or more precisely, the ratio of those two, tells you something about how much less efficient MCMC is in a Monte Carlo sense as a function of its having autocorrelated output than if we had been able to figure out how to do IID sampling. IID sampling is quite difficult to do in this problem and would be nearly impossible to do in problems of even greater complexity than this one. And then in the second unit of what's going on here, he gives you quantiles for each variable, various percentage points in the distribution. And so you can get 95% intervals by going from the 2.5% point to the 97.5% point. And if you wanted to compare the Pasteur median 404.295 with the Pasteur mean for mu 404.297, that's an expression of how symmetric the distribution is, for example. We can see thereby that he's giving us more or less the same stuff that we would have been interested in my homegrown code. And then I can do the same thing for the single sample, the single thread example. And the results here should all be virtually identical apart from Monte Carlo noise, and just taking 3.5 times longer to actually produce. So if you compare any particular part of this with the story that we got from the quadruple threaded story, look at the output for y.nu, for example. The quantiles are similar apart from Monte Carlo noise. We saw that the typical standard error, Monte Carlo standard error for y.nu is on the order of 0.02. And so you can see that the numbers from one chain, from the single chain, 416.016, compares with 415.95, and indeed they differ from an amount that's comparable in size to the Monte Carlo standard error. So that's just noise arising from the sampling process. So there you go. You now have a template for courtesy of Chris for parallelizing anything that you would have gone ahead and written either in WinBugs or in RJAGs. You now have a template for parallelizing it, and the limitations are just the limitations of how many CPUs you have available. I think I have 8 CPUs in this particular box here, and so I could have actually run things even faster. So that's an example which I hope you'll find useful. This permits us to tackle problems of much larger scope. Later in the quarter, I'll show you an example of modeling data where the outcome variable is dichotomous. It's whether or not babies at the Kaiser hospital chain end up, particularly babies who are premature, newborns who are born with low birth weight and in real medical difficulties, whether they or not they develop a horrible condition called sepsis, which used to be called blood poisoning and is actually better described as full body infection. I have a data set on about 70,000 babies with 3 quantitative predictor variables to try to use to predict which babies are going to get sepsis. The whole idea at Kaiser, as I may have mentioned before, is the tremendous focus, which is why I like working with them so much, is always on preventing bad things from happening before they happen, rather than waiting for the bad thing to happen and trying to fix it afterwards. And particularly with sepsis in newborn, particularly premature newborns of the kind that would go to a neonatal intensive care unit, if you wait until it's already happened, it's done. Either the baby dies right away, or else the baby ends up lapsing into a vegetative coma, and which is sort of worse than death, and there's no way back. Current medicine doesn't know how to fix that. So with a condition like that, the only chance that you have is to keep it from happening in the first place, which means that we want to use variables that we gather on the baby in the first few hours after birth to try to accurately predict which babies are going to go septic in order that we can hit them with a really strong dose of antibiotics and do other things that will help to try to prevent it from happening. MCMC with 70,000 observations in a logistic regression sort of setting with a single thread would take long enough that you wouldn't want to watch it run here in the demo part of things. But that same MCMC with 8 CPUs, I think I'm going to be able to show you good results in half an hour, for example, or that I can run it over lunch and show you what's happening. So that's an example of where we're headed by being able to use this parallel MCMC. In fact, I think I will tell you about the issue of non-identifiability now, because it fits in with some stuff we talked about earlier. What I've done is I've created a little artificial data set that stands for the sort of thing you would get if you took a random sample of adults and measured their IQ on the Stanford-Binet scale. It turns out that the scale is normed so that it has a mean of 100 and a standard deviation of 16. And the scores turn out to be remarkably close to, their distribution is remarkably close to normal. So I create a sample size 50 from a normal distribution with mean 100 and standard deviation 16. And I round those numbers to the nearest whole number and I sort them. And I put that in a vector called y and I print the result. So unfortunately, I forgot to use the set seed command. So if you ran this code, you wouldn't get the same numbers as I do. But if you tried to run it and then use the R code, or rather the Winbugs code I'm about to show you, you'll get results that are qualitatively similar to what I have, not exactly the same numbers. And it turned out here that the sample mean was indeed quite close to 100, and the sample standard deviation was indeed quite close to 16. And then I used the dput command to output this file, and I'll show you what the file looks like when you do that, because it's very easy to go from the dput command into what you actually need in order to be able to get things into Winbugs or into RJAGs. So the result of running the dput command is it simply prints out the data values separated by commas and collected together into one of those collect operators, just like in R, but that's the same way that the data is supposed to be organized as far as Winbugs and RJAGs is concerned. So all I have to do to get that ready for R, or rather for Winbugs or RJAGs, is to say list, open parenthesis, if I can spell, y equals, and now that defines the y vector, comma, n equals 100, close parenthesis, and now that's the data file. So it's actually quite easy to take the output from R with the dput command and bring it directly inside your Winbugs or RJAGs. So let me go ahead and grab the model file for the Winbugs work, and I'll fire up a copy of Winbugs. I'll show you what I have in mind. So as usual, I get rid of that file there. I go back to the course web page and I capture the model file and go into Winbugs and open a new little window and paste it in there. And as usual, the text is too small, so I'll blow it up to 12 point and resize the window. Is 12 point large enough that that can be seen well in the back of the room, or should I make it even larger? Can you guys see it more or less okay? Okay. Well, it would be pretty natural to fit a model here where your sampling distribution, which defines the likelihood function, would involve looping across the data values and having y sub I be a draw from a normal distribution with parameter, mean parameter mu and precision parameter tau, as we've talked about before, where tau is the precision of the distribution 1 over the variance. Suppose I perversely instead tried to focus not on mu, but an additive decomposition of mu into mu dot 1 plus mu dot 2. And I tried to put a prior on mu dot 1 and a prior on mu dot 2. Of course, I would need to put a prior either on tau or sigma squared, and I've chosen to use a uniform prior on sigma, and then define for R later on down here that tau is the same as 1 over sigma squared. And I've also decided to create draws from the predictive distribution into a place called y dot predicted in the way I've shown you before. So this model, as I've written it, has the following quantities of interest floating around in it: mu1, mu2, sigma, tau, y dot predicted, and mu. So those are the things floating around. They're the nodes in the graph, so to speak. Okay. Intuitively, should we be able to learn about mu from the data in this model? I give this model 50 observations. I should be able to learn quite a bit about mu. Should I be able to learn about tau and therefore also sigma? Certainly. Should I be able to learn about the predictive distribution? Certainly. But can I learn about mu1 and mu2 separately? Is there any way, if you choose to additively decompose mu into the sum of two things, is there any way to learn about those separate components? If all that the data has to say is about mu, it's like asking, I have a number, and the number of interest to me is 7. Unknown to you, I got that number by adding two numbers together. Now you have to guess which two numbers I added together to get 7. Can you do it? No. Will there be any information in the data about mu dot 1 and mu dot 2? Having parameterized in this way, will there be information in the data about mu, or does the fact that I did this weird thing cause the sampling to go wrong? If I do it right, mu is what people call identifiable. It's a parameter that we are capable of learning about it from the data. All of these parameters, mu tau, sigma, and y dot predicted, they're all unknowns that can be directly learned about from the data. Mu1 and mu2 are called non-identifiable because there's no way to learn their values from the data. And this is the kind of structural non-identifiability, namely that no matter what data set you put into this model, you will never be able to learn mu1 and mu2. So that's an example of a model that has parameters in it that are non-identifiable. And that sometimes happens without you meaning it to happen in complex models. How will this play out in the Bayesian story? Will WinBugs refuse to compile this model because it has non-identifiable parameters in it? Turns out no. Will it refuse to actually run and do the MCMC sampling because there are non-identifiable parameters in there? The answer turns out to be no. But just use your common sense and tell me what we should get. If there's no way to learn mu.1 and mu.2, and yet we're going to get posterior distributions for them out of the MCMC sampling, then how will that express itself? The posterior for mu.1 should look like what? It shouldn't look flat unless I had done something to make it flat. What would be the Bayesian equivalent of there being no information in the data? Think about Bayes' theorem. Posterior equals prior times likelihood renormalized. If there's no information in the data, the likelihood function is what? Is it highly peaked or does it tend to be diffuse? If there's no information in the data about a parameter, the likelihood function is flat. Therefore, if you have non-identifiable parameters in the model, nothing will go wrong with compiling the model and doing the MCMC. But when you're done, the posterior distribution for any non-identifiable parameter will have what relation to the prior? Identical. Absolutely identical. So this is the Bayesian sense of non-identifiability. You can perfectly well fit models that include non-identifiable parameters, but the diagnostic for it is that the posterior will coincide with the prior. That sometimes happens even when parameters are identifiable in a strict sense. It should be possible to have information in the data about that parameter, but in some cases the data set is too small to actually be able to learn those parameters. And I'll show you an example of that later on. So we have two different kinds of non-identifiability. I'm going to call one of them structural non-identifiability, this one here where no matter what the data set is, you can't learn those parameters. And we'll call the other, for a want of a better word, no one seems to have any actual officially recognized terms for this. We'll call the other kind non-structural identifiability. And what I mean by that is that it is possible to learn this parameter with enough data. But if you have a data set that's too small, you can't learn it.
Question.
Yes, please.
So in your consulting,
No, not intentionally. You generally don't want to fit models that have non-identifiable parameters in there because there's no point in doing so. But you may, without meaning to, formulate a model in such a way that one or more of the unknowns in your model are non-identifiable. And we now understand a very simple and straightforward diagnostic for that in the Bayesian paradigm. What kind of information would you know that you said that mu1 and mu2, if you knew that they were different, would that express itself by knowing, for example, that mu2 is larger than mu1, for instance, or smaller, or just unequal to? How would that play out? The information that mu1 and mu2 are unequal does not provide any information in the likelihood function. If you were going to try to have this parameterization have real likelihood information, you would have to put in something stronger than that. And even if you tried to put in some kind of monotonicity arrangement where in the prior mu1 has to be smaller than mu2, you'll still find that there's no information in the data because there's an infinite number of different mu1s and mu2s that all add up to the mu that we're getting from the data and still have mu1 smaller than mu2. So the only way to make mu2 identifiable, actually no, there's no way in this model to make mu2 identifiable. I can put as strong a prior as I want on either mu1 or mu2, but we're not going to be able to learn them separately. So let's see how it goes, and then I'll write some of what I just said down here on today's extra notes. So let's go ahead and get the data set in. So I'll get another new window here, go back to the course web page and grab the data file, which, as I showed you, was arrived at by using the dput command and a little bit of editing afterwards. Let's go back into WinBugs and put the data in there and bring it up to 12 point so we can all see it. Make that window a bit smaller. And then I'll come up with another new window and go back and grab the initial values. Now, just to show you that the initial values themselves can have no positive possible effect on this, I've chosen utterly generic initial values. And here's what I mean by that. If you wish to ensure that all that's necessary is a small burn-in period, then you will try to initialize the Markov chain at values that are similar to what you will find are close to the posterior mean or mode, some sort of measure of center of the posterior. But all that will do is make the length of the required burn-in period to reach equilibrium smaller. What I mean by generic starting values is you think about a parameter and ask, can it live anywhere on the whole real line? If so, you give it a generic starting value of 0. If instead it can only live on the positive part of the real line, you give it a generic starting value of 1. These are sort of default values that people tend to use. If the parameter can only live between 0 and 1, then what do you suppose the generic starting value would be? A half. And so basically, I'm starting these chains off at places that actually are not at all well supported by the data, because mu is actually around 50. And mu1 plus mu2 in the in the starting initial values is 0. And sigma in the data set is going to come out around 16, and yet I'm starting it at 1.0. And y dot predicted is going to be a distribution centered at 50, and I'm starting it at 0. So I'm deliberately starting it in places that are far from the equilibrium values just to see what happens. So I go ahead and get myself a specification tool like usual. I foreground the model and check it. And I foreground the data, and it says data loaded and compile. I get the model compiled story. I go ahead and click on the initial values and load them, and I get that, as I've mentioned before, much to be desired expression model is initialized. So I kill off the specification tool as usual, and I choose the update window. Now I'm going to do something new just to show us the nature of the burn-in process. I'm going to ask it to refresh after every one iteration. Yes, did you have a question or comment? Okay. And initially, I'm only going to update one observation at a time. And in order to actually see what happens, I'm going to start the monitoring now. So there won't technically be any burn-in period because I'm going to start the monitoring now. So let's monitor everything we care about, mu.1 and mu.2 and sigma and tau and mu. Pardon? Okay. And y dot predicted. What's your comment? That's right. That's right. And the reason for that is that even though I always organize my model files the same way, namely prior at the top, sampling stroke likelihood loop in the middle, and derived values at the bottom, that is not the way WinBugs processes it. You can put that stuff in that file in any order you like, and it will have the same exact logical effect on the model. So you're right. If WinBugs were reading from the top down, it wouldn't know what mu is because mu hasn't been defined yet. But as long as there's some statement somewhere that deterministically links mu to stochastic nodes mu1 and mu2, then it's okay.
Oh, that's because it has to construct the graph anyway.
It has to construct the graph anyway, so it doesn't matter the order in which you put the stuff in there. I've never tried taking one of these things here that's deterministic and sticking it inside the sampling distribution loop just to see what would happen. It might well complain about that. In fact, if I were building a graph, I think I would complain about that. But apart from doing that, you can put that stuff in there in just about any order you like, and the same model will result. Now that we've defined all these nodes, let's go ahead and pick each one and hit the command called trace. And let's start watching the dynamic trace for each one and see how they unfold. So there's mu.1. I'm going to get a trace for it also. And mu.2. Trace for it as well. And sigma, the trace for sigma turns out to be interesting. That up here, maybe I'll put that down a bit farther. And we could even look at tau. On this little smaller version of my window on my machine, I'm not able to see as many of these things as I might like. And as I mentioned to you before, WinBugs thinks that the monitoring tools and the update tool are so important that it won't let anything right over top of them. So maybe I've sort of reached the limit of the things I can actually look at. Let's get rid of tau anyway because it's a deterministic function of sigma. But let's see if we can look at y.new or y.predicted. And I don't know, I'll tuck that over here somewhere and hope that we can look at it a little bit.
Probably push the monitor.
I probably could. You're probably right. Now that I'm done with it, I could probably put it way over here, and I don't even have to look at it. You're right about that. All right, so I'm going to hit the update button and see if it will update one iteration. That's funny. The dynamic traces are not showing us anything. This worked this morning when I was trying it. Let's try putting in 10 and hitting update. Okay, so this is now updating from really bad starting values, the first 10 iterations of what would have been the burn-in period, except we're watching it to see what it looks like. Mu1 started at 0, and yet in a very short period of time, actually its very first value seems to have been down around minus 1,000. And then in a very short period of time, it starts sampling rather close to, we're going to see it'll sample rather close to 50. So it jumps in a very short period of time. Look at sigma, for example. Even though its value in the original initial values data set was only 1, it jumps all the way to 25 in the very first iteration, and then the second one, it already is dropped into equilibrium. It's already dropped all the way down to 16. And so this is an example of what I was telling you about last time. People often use default burn-ins of length 1,000 or whatever. In many of these models we're working with, you hardly need any burn-in at all. The thing is essentially in equilibrium right when you start. The y.predicted values may start out at some slightly funny numbers, but pretty quickly they jump in and get around the value of 50 they should be in. And interestingly, mu, it starts out at, let's see, yeah, that's right. I've got the correct value to be 100, and so it starts out in equilibrium right from the beginning, even though I started mu1 and mu2 both out at 0. So I could do a little more dynamic tracing for you. I could show you a little bit more and a little bit more, give you 100 this time. And essentially what you see is that we didn't even really need a burn-in period. Maybe one iteration for sigma to go from a stupid value down to where it really belongs. So very short burn-ins required. So that means I can pretend there is no burn-in, just throw it away, and I'll go ahead and get a whole bunch of draws from each one. So let me do that now. So I'll go ahead and kill all the trace windows because they really slow the sampling down. And go back and ask it for 100,000 iterations, for example, refreshing every 1,000. And why aren't you moving? There we go. And that actually goes very quickly indeed, as you can see. And it took 6 seconds to get 100,000 iterations. And now we can begin and see whether we get the results we expected. We all thought that mu was identifiable in this model, and so we should be able to learn that mu is around 100, even though the prior for it amounted to something centered close to 0. And in fact, if we look at the density, we get a Pasteur distribution for it that looks roughly Gaussian, centered right at 100. And in fact, the Pasteur mean is about 100.1, and the Pasteur standard deviation is about 2.33. Using ordinary frequentist logic, we would think that the sample mean, I think I showed you what the sample mean was from the data file back here. So the sample mean was 100.14, and the Pasteur mean comes out 100.1. If we had another digit, it would probably be 100.14. And the sample standard deviation came out right at about 16, and we know the frequentist answer for the standard error would be 16 divided by the square root of 50. That's the usual S over the square root of n sort of thing. Didn't I do 50 observations? I think I did. And so we expect the frequentist standard error of about 2.26, and that matches almost perfectly the Bayesian Pasteur standard deviation, about 2.3 in both cases. So we have learned perfectly about mu, even though it's composed of two things, mu1 and mu2, that are not identifiable. Similarly, we've learned perfectly about sigma. Its Pasteur distribution has a long right-hand tail, as scale parameters generally will, and its Pasteur mean is right around 16, just like the sample standard deviation was. So we've learned quite a lot about sigma from the data set, and y dot predicted is behaving very naturally. In fact, just a rough idea of the predictive distribution for a new data value should look a lot like what in relation to the data set itself. The predictive distribution for a new value should look like what in relation to the actual data. It should look a lot like the same sort of thing that the data is showing us. The data set has a mean of around 100 and a standard deviation of around 16, and so the predictive distribution should have a mean of around 100 and a standard deviation of around 16, and it does. And in fact, that distribution, if we plotted it, looks quite a lot like the data distribution. So that, no wonder. I mean, the model fits the data quite well, and so the predictive should look a lot like the data set. But now if I look and see what happens to mu dot 1, I discover that the Pasteur has sampled values across the 100,000 iterations that run down to about minus 3,000 and up to plus 2,500 or 3,000. No surprise, because I gave it a normal prior with a mean of 0 and a precision of 1.0 times 10 to the minus 6, which is like a variance of 1 million, 1 over 1.0 times, in other words, 1.0 times 10 to the plus 6, which is a million. And therefore a standard deviation of about 1,000, square root of a million. And so what I'm saying in the prior is that I think mu1 could be more or less anywhere between minus 3,000 and plus 3,000 by using the empirical rule, going roughly 3 standard deviations either way. And that's what it says. The prior and the Pasteur coincide almost perfectly, with one exception, interestingly. The Pasteur standard deviation is huge to reflect the fact that we don't know much because the Pasteur and the prior are virtually the same. But it has decided that the Pasteur mean is around 50 in this model. And if we ask about mu2, we get virtually the same exact density. Oops, I didn't mean to do that. If I show them both next to each other, they're virtually the same exact Pasteur density. And the mean, again, comes out right around 50. So what has happened is that no matter where we started it, in this case we started it off at 0, 0, which has nothing to do with it, the MCMC work, the modeling process, has decided to evenly split the difference. The right answer for the mu1 plus mu2, is 100, and it's just decided, okay, I'm going to give each one of them 50. So I'm not sure we would have been able to predict that, but anyway, what we are able to predict is that as far as spread in the Pasteur is concerned, it's identical to the spread in the prior. We've not learned anything at all as far as the uncertainty bands are concerned. And so that's how non-identifiability plays out in a model where you have, without meaning to perhaps, put in parameters that are unidentifiable. Is what a heuristic within WinBugs? I don't have a ready explanation for why that came out that way. We know that whatever it ends up deciding, the posterior mean from U1 plus the posterior mean from U2 should be around 100, because that is the right posterior mean for mu, which is its sum. But I'm not sure, I don't know why exactly it's decided to split the difference. I'd have to think about that. There's probably a good mathematical reason for it, and I'd have to think about why. So let me summarize a bit of this over here on the on today's extra notes. It'll come up like this thing has sagged a bit since it was actually installed. So Bayesian non-identifiability, corresponds exactly to the simple diagnostic of for a parameter theta corresponds exactly to the fact that the posterior for theta has the same uncertainty built into it as the prior for theta. In other words, the likelihood function has not told us anything in terms of decreasing our uncertainty. And we can make a distinction between two kinds, structural, I'll call it structural non-identifiability, and what that is going to mean is that cannot learn about theta from the data no matter what the data set is. If I go back to this Winbugs example, and I give you a new IQ data set in which instead of having 50 observations, I had 50,000 observations, would the non-identifiability of mu1 and mu2 go away? The posterior and the prior would be the same. So this is structural non-identifiability. No matter what the data set is, you won't be able to learn mu1 and mu2. In contrast, we're going to see at least one example in a while of what I'm going to call non-structural non-identifiability. That's a long word. It's a mouthful. And I did one of those plan ahead things. I didn't plan ahead in writing the word. Non-structural non-identifiability, what I'm going to mean by that is that can learn about the parameter if n is large enough, cannot if n is too small. So we're going to have the same sort of phenomenon where the posterior and the prior coincide for some models where there isn't anything structurally non-identifiable about that parameter. In principle, you ought to be able to learn that parameter. It's just that you don't have enough data yet to actually have enough information in the likelihood function. We'll see an example of that later on. Okay, so I'm going to go ahead and just kill that off. I don't want any of these things. Let them go. Kill that off too. Going back to the course webpage, I'm going to save this last example for later when it arises naturally in what we are doing. So let's return now to the story about hierarchical modeling that we were working on last time. Thanks. I have, I'm afraid, slightly forgotten how far we got in this, so I'm going to need your help a little bit. Let me remind you of the case study. Our first case study was a meta-analysis of the effect of aspirin on subsequent death for people who have already had a heart attack. And those of you who listened to NPR, this was back in the news again just in the last couple of days. Did you hear the story? It was on the morning NPR show. They were talking about who should, or maybe it was one of the talk shows, maybe it wasn't actually on All Things Considered or NPR Morning Edition. On one of the talk shows, they were talking about who should take an aspirin and who should not. And one thing that's definitely important to emphasize is that children should not take aspirin at any dose. Do you know why? Has this come up in your lives? There's a disease, there's a condition that aspirin can cause that is very harmful for children. I forget the name of it. Is it Ray's or Rye syndrome? Yes, okay. And so children should not take aspirin at all. There are other non-steroidal anti-inflammatories than aspirin that don't give rise to that condition that work better. People who have had a heart attack already should definitely take aspirin. That's the result of this meta-analysis and others. And the dose should be chosen by you and your doctor in a way that's just the right amount. If you've got too little of it, then your blood doesn't get thinned enough to get the health effects in holding off strokes and further heart attacks. And if you have too much, then you've thinned the blood too much and you get things like bleeding ulcers and so on. So there's a little bit of a knife edge to find, and you and your doctor can work on that together to find the right dose. For most people, what used to be called a baby aspirin, which, by the way, is no longer called that because of Rye syndrome. It's not good to call it a baby aspirin because you shouldn't be giving aspirin to babies. What's called a baby aspirin, and it might still be called that if you go to CVS or someplace, the bottles might still say baby aspirin on them, even though they're not supposed to anymore. It should say something like low-dose aspirin. That's the official name that people are supposed to use now. That, I think, is something like a third of the usual dose in each pill in a standard, or maybe a quarter of the usual dose in each pill of a standard aspirin. And I think that's a starting dose for anybody who's already had a heart attack, namely one of those low-dose aspirins a day. That's a little bit of blood thinning. If you haven't had a heart attack, but you're over the age of 60, most doctors recommend taking one of those little low-dose aspirins a day also, anyway, prophylactically, because it can thin the blood just a little bit and help prevent heart attacks. And all of these results, all of these conclusions, current wisdom of the medical profession were arrived at on the basis of meta-analyses like the one that we're looking at here. So you recall the setup. We had a series of 6 different experiments, all of the same phenomenon. They were all randomized controlled trials with what's called 2 arms in the study, an aspirin arm and a placebo arm, placebo being a pill that looks just like aspirin but doesn't have any aspirin effect in it. People were randomized, in the case of UK-1, 615 of them to aspirin and 624 to placebo, and followed for a period of time. All of them had a previous heart attack, and they were followed for a period of time judged to be long enough to see whether aspirin really made a difference or not. I don't remember how long that was. And we find in 5 out of the 6 studies there was a noticeable decline in mortality for the people in the aspirin group, on the order of about 2 percentage points, which is an enormous difference. And yet the last study, AMIS, American Myocardial Infarction Study, is that right, Chris? Was much larger than all the other ones and went exactly the other way, with aspirin appearing to make things slightly worse. So the question becomes, if this is the totality of your information, as it was back in the time that this was done, I think we were working with this in the late 1980s, early 1990s. If this is the totality of the information that you have from all possible studies, turns out there were 6 at that time, how can you combine the information from those studies in a way that produces a result that is a better information combination than the information from each study by itself? That's the discipline of meta-analysis. And I mentioned to you last time that it's going to be very natural to work out the difference in mortality rates. Let's do it in the order of placebo minus aspirin to get a positive number for most of the studies, and to work out a frequentist standard error for that difference in the usual way based upon calculations involving 2 independent samples. Those numbers are going to be important to any analysis you would do, Bayesian or frequentist. And a very naive thing to do, which we agreed was a bad idea, is to simply take all 5,600 people in the treatment group and all 5,200 people in the control group and put them all into 2 giant columns. So there's a big column of treatment numbers and a big column of control numbers by completely naive pooling all those data sets into one big data set, and then calculate the mean difference, for instance. So what happens when you do that is that you are pretending that there is no between study heterogeneity, when we can see manifestly that there's quite a lot of between study heterogeneity. In effect, what happens is that the Amos study swamps what's going on because it has so many more patients in it, and that's actually a very poor estimate of what the actual effect of aspirin is. That turns out, as we saw, to be a special case of the right thing to do, in which you somehow pretend that you know that there is no between-study heterogeneity. And a far better idea is to fit a model that includes the possibility of between-study heterogeneity and look at the posterior distribution on the parameter that governs the heterogeneity and see if it has support near zero. And if it does, then maybe it's okay to do this naive pooling. But we're about to find from a Bayesian analysis that it has no support whatsoever in the data. And so I mentioned last time that people have often, before contemporary work, have often tried to use methods based on the usual sort of signal-to-noise ratio, z-scores, and computing p-values from them, and trying to combine the p-values in some intelligent way, including people like Fisher were interested in things like that. But that's not a good analysis of the data because your answer comes out on the p-value scale, which is an artificial probability scale. You want your answer to come out on the scale of percentage points of mortality improvement. That's the thing that counts. BC Ops, we're about to start again here now at 10:15 and go for an hour from 10:15 to 11:15. Thank you. May we begin again, please?
We're recording.
Thank you. Somebody brought up an interesting point during the break. Namely, the question was, he was thinking of another situation where naive pooling gives bad answers. And so, namely Simpson's paradox. You guys have probably seen Simpson's paradox examples before. Can we begin again, please? You may recall that Simpson's paradox is one in which it appears, for example, that a treatment is good for men separately, and that same treatment is good for women separately also, but when you combine men and women together, the treatment appears to be bad. And so, how can this happen? And the answer is, well, I've written a little bit here that we may find helpful. Heterogeneity between studies yielding conclusions that naive pooling is wrong, which is the sort of thing we're talking about here with the hierarchical modeling, is not the same as Simpson's paradox, which is another setting in which naive pooling can be silly. And Simpson's paradox is usually exposited in the context of 2x2 tables, but I like to think instead in regression terms, which is something that, in fact, it turns out to be not a paradox at all when you think about things from a regression point of view. So suppose you have observational data, not randomized control data. So you've just observed an outcome Y, and you've observed a supposedly causal factor, X1, on all the people in your study. And you fit a naive regression in which you regress the outcome linearly on the supposedly causal factor. So the model is going to look like yi equals beta 0 plus beta 1 xi1 plus an error term ei, which is usually assumed to be as an off-the-shelf assumption, IID normal with mean 0 and variance sigma 1 squared. And suppose it turns out that the sign, SIGN, of beta 1, that coefficient, is positive. That would suggest to you that you should draw the conclusion that if you were trying to make a causal conclusion from observational data, which, as you know, is always a dangerous thing to do, that would lend you to believe that it would lead you to believe that increasing x1, causing an increase in x1, would cause an increase in y because the sign of the coefficient in front of x1 is positive. However, we all know, at least those of us who have had to work with data of an observational character, we all know that, in fact, in addition to a supposedly causal factor in observational studies, there will typically be one or more other factors that are also possible causative agents. And people in epidemiology call them confounders, or another name for them would be potential confounding factors. So I have a supposedly causal factor, SCF, X1, and I have one or more potential confounding factors, x2, in this case here, just one of them. Now, if I try to regress y both on x1 and x2, I have to be careful writing the model down, because when x2 is in the model, the coefficient in front of x1 does not have the same meaning. In the model where x2 is not present, the coefficient beta 1 in the model where x2 is not there represents the average effect of changes in x upon y. However, when x2 is in the model, the coefficient, which now has to be called beta 1 star or some other name than the beta 1, that coefficient now represents the average effect of x1 on y after adjusting for the effect of x2. And that can be quite a different thing. Also, the intercept could easily change when you bring in x2, so I have to use beta 0 star down here. And the error terms are certainly going to be different now. They used to be called EI, now I could call them epsilon I, for example. And it would still be customary to assume that the epsilon i's were IID normal with a mean of 0, but they're going to have a different variance, typically smaller, because x2 has explanatory power, and so the variance under the model that does not have x2, sigma 1 squared, will typically be bigger than sigma 2 squared. But what happens with Simpson's paradox is that it's very possible for the sign of the coefficient in front of x1, beta 1, when there's no x2 in the model, to go from positive to negative when x2 is present in the model. And the result would be that you would actually think that after adjusting for x2, the average effect of x1 is a decrease in y rather than an increase. That would be a bit of a shock, right? But in fact, it's perfectly possible. Just because you forget to put in a variable that's important in a regression doesn't mean that the coefficient you're going to get on it is a worthwhile thing to look at. Here in this model, if x2 really was a PCF, the negative coefficient, beta 1 star, will be a far better summary of the average causal effect of x1 on y than the positive coefficient, beta 1, if we hadn't brought in that confounder x2. And so that's what happens in Simpson's paradox in the setting in which the drug looks like it's better for men and it looks like it's better for women, but it's not better. It looks like it's worse for them together. Without bringing in the PCF of their gender, that would be a beta 1 that had a minus sign, made things worse. But bringing in the PCF of gender, now all of a sudden there's a plus sign. And so the overall conclusion that the drug is worse overall just arises from this top naive regression. So this is the bad regression up here, where we haven't brought in the PCF. And this is the better regression down here, in which we adjusted for it. We remembered to actually measure a PCF and adjust for it. Of course, having thought of one PCF and noticed that it made a dramatic change on the results, our appetite for PCFs should be stronger than just one of them. Our job should really be in trying to figure out what the actual causal effect of X1 is on Y needs to be to collect all of the PCFs that we judge to be relevant to the story from a possible causal point of view, measure all of them and adjust for all of them. And when you're done with that, you can begin to believe that maybe the coefficient in front of X1 does tell you something about the actual causal effect of X1 on Y. But of course, that's a hard thing to do, right? Because you can't always think of what all the PCFs are. And even if you can think of all of them, you might not have measured all of them. And that's the trouble with observational studies rather than controlled experiments. This sort of thing can never happen because gender in a controlled experiment would have been balanced by the randomization process. And so X2 could not act like a PCF in that context. And so you're always sort of trembling, publishing results from an observational study, trembling, waiting for someone to come along and say, but look, there's an important PCF that you forgot to measure and adjust for. And I'm prepared to believe, the person who's your critic, I'm prepared to believe that if you had measured it and adjusted for it, the actual effect could have gone away completely or even reverse sign yet again. And so you have no good way to rebut that person other than to go ahead and try to collect that PCF and bring it in as an adjuster. So it's very dangerous to try to draw firm causal conclusions from observational data because there are probably PCFs that you haven't thought of and you forgot to either measure them or you forgot to adjust for them in the modeling process. Anyway, that's Simpson's paradox. that involves a different kind of naive pooling. Here, the regression that has no X2 in it, where X2 stands for gender in this example I gave before, the data have been naively pooled by forgetting to pay attention to what the gender was. And as soon as we separate it out and adjust for it by putting it in as a predictive variable, the coefficient actually changes sign. That's Simpson's paradox. But that's different from the sort of problem we're seeing here in meta-analysis, where heterogeneity can, in fact, give rise to a different reason why naive pooling is bad, namely that naive pooling gives the wrong amount of weight to each study that should be pulled together. In particular, since Amos is so different from all the other studies, we have reason on the basis of the other 5 studies to doubt its conclusion.
Which path?
Oh, I'm sorry, thank you. Really bad at that. So in particular, since Amos's conclusions were so different from all the others, the fact that the 5 other studies went exactly the opposite direction and rather strongly so indicates to us that actually we have pretty good reason to doubt the results from the Amos study. And so far from giving the Amos study almost 50% of the weight in the naive pooling, instead we should be giving it much less weight than that to reflect the fact that in fact, it seems to be anomalous. It seems to act like an outlier. That's a good thing. We need to hit this with a lot more tape to keep it from being on the move. Okay, so that's the background here, and we got a certain distance into this. I showed you the standard Gaussian hierarchical model for this, in which we have a model for the data at the bottom level of the hierarchy, and we have a model for the so-called random effects at the middle level of the hierarchy, and then we have a model for the parameters that index the distribution for the random effects at the top level of the hierarchy. So our basic story is to think that y sub I, which you'll recall is the difference of placebo minus aspirin for study I in the observed mortality rate expressed in percentage points. So y sub 1 is 2.77, and y sub 2 is 2.50, and so on. Those are the y sub i's, and our model for them is that each of them has its own underlying tendency to produce a certain value. If you had run that same particular study with a much larger number of patients instead of the patients you had, the sample sizes you had, and you kept the same study protocols exactly, treatment protocols, and you kept the same exact method for gathering patients into your study, patient cohort, then study I would have its own underlying so-called true effective aspirin for studies like that one. We'll call that theta I. And we think of the y sub i's as like independent random draws from normal distributions where each y sub I has its own theta sub I. And then, of course, each normal distribution has its own variance also. And we can use those v sub i's that we got by taking the standard errors and squaring them to get the amount of variability for the y sub i's around their mean theta sub I. So this number here, which we got by ordinary frequentist means using a calculation based on a right triangle and so on, I showed you that last time, that number is something that we're going to pretend in this modeling is known, because in fact that number is based on hundreds or thousands of patients, and so it has actually quite a small amount of uncertainty attached to it. You could elaborate this model by thinking of the v sub i's as unknown, but you would find that that didn't change the conclusions very much. So that's the data layer, and the basic thing that the model is trying to say at the data layer is that every study has its own propensity to come up with a different underlying effective aspirin, and we would try to explain those differences scientifically by appealing to potential differences in patient cohorts and potential differences in treatment protocols. Then you need a model for the theta sub i's, because as we've talked about repeatedly in here, we have 6 studies. You cannot fit this model down here at the bottom level because you have 6 observations and 6 thetas, and there's not enough information to be able to learn each theta. So now we have to have a model for the thetas that describe somehow what we know about them, and that will allow us to actually learn the parameters that we care about in the model. So as I mentioned last time, and as I'll show you an example of today, if we had any covariates at the study level, what we'd want to do would be to build a regression model at this level where we regressed or we tried to predict the theta i's from some study level covariates. But we don't have any study level covariates in this study. All we have is just the actual summary numbers for each study. And so we're going to write down a model that acts like a regression, except with only an intercept term in it. And that corresponds to thinking of the theta i's as like IID draws from a normal distribution with an underlying mean mu and an underlying variance sigma squared. And that is the embodiment, that is one particular possible embodiment of the Bayesian judgment that before you saw any of this data, your uncertainty about the theta i's would have been exchangeable. In other words, you wouldn't have known why it would be that study 5 would have a bigger or smaller theta connected with it than study 2, for instance. And as we've seen in other modeling, one of the most natural ways to embody the Bayesian judgment of exchangeability is to take the quantities that your uncertainty is exchangeable about and regard them as like IID draws from a common distribution. That's essentially a good way to embody the idea of exchangeability. And the normal assumption at the bottom level here, as I mentioned last time, is actually founded on good science because we have thousands, hundreds and thousands of observations, means taken across hundreds and thousands of observations of ones and zeros to get these y sub i's here. Each of them is a difference of two means, where each mean is based on hundreds or thousands of patients. And so we know by the central limit theorem that they are really going to be normally distributed. So the n in the bottom layer of this model, I'm very proud of. I'm quite happy to go with it because the central limit theorem tells me it needs to be there. This n right here, in fact, is not something I'm particularly proud of. It's just a conventional assumption. People always assume this right here just because it makes the arithmetic easier. Now later on, and I think we talked about this briefly, I'll show you what happens if we try to replace that normality assumption with something that might seem more natural, namely, looking back at the Amos study, it looks like an outlier, doesn't it, in relation to the other ones? And so it looks sort of like the distribution of the thetas is heavy-tailed. And so instead of modeling it with a normal, what would be a natural thing to model it with, following on from the NB10 study? Why not model it with a T distribution with unknown degrees of freedom? And what we're going to see when we do that in MCMC later today is that when you try that, you get into one of those situations of non-structural non-identifiability. The data with only 6 studies has precisely no information in the likelihood function at all for learning what the degrees of freedom are in the T model. So that's yet the prior and the posterior on the degrees of freedom parameter are identical. And so that's another example of non-identifiability except of a non-structural case. If instead of having 6 studies, we had 100 studies, we would have been able to learn that degree of freedom parameter the way we did in the NB10 study. All right, but we're going to go with the normality assumption because we can't really challenge it on the basis of the data. There's no information for trying something different. And the parameters of this normal distribution are crucial in this model. Mu represents the overall underlying effect of aspirin on heart attack. So mu acts like our grand mean. It's the number that we care about coming out of this modeling. What we as doctors, for example, would use to decide whether to give a patient in front of us an aspirin or not, someone who's already had a heart attack. And the parameter sigma is a very important parameter because it represents the between study heterogeneity on the standard deviation scale. Sigma says how variable the theta i's are. If sigma were somehow known to be 0, then how would the model change? What's a normal distribution with a variance of 0? What's that look like? It's a point mass. It's a constant. And so that would be like saying that the theta i's are in fact identical to each other. And that would turn out to correspond to the naive pooling idea. Because if all the theta i's are the same, then it's perfectly okay just to toss all the treatment data into one big pot and all the control data in another big pot and go from there. But what we're going to do is we're going to fit a model in which we allow learning about sigma or sigma squared from the data and look at the posterior distribution and see if it has any support anywhere near 0. And the answer is going to be no. It's ludicrous to think of sigma as 0 in this model. And then, of course, in the Bayesian sense, we have to put, as usual, a prior on the mu and the sigma squared. So I showed you how to, with the jargon, the theta i's are called random effects. Another name for them is latent variables, where latent means unobserved. There's no way in this model ever to actually see the theta i's, but the y sub i's act like observable shadows of them. We get a sense of what the theta I is by looking at the y sub I, but we'll never actually be able to see the theta I. So it's a random effect or a latent variable in this modeling. And if you pretend that all the thetas are the same, people call that a fixed effects meta-analysis model, whereas if you allow for the possibility of heterogeneity, they call it a random effects meta-analysis model. And the basic Bayesian takeaway message here is it's always better to fit the random effects model and then see if it looks as though the posterior distribution on sigma is close to 0 or not. And that could serve as a good excuse for trying the fixed effect story, but never the other way around. And in fact, for years, it was the practice of people in disciplines like economics and to some extent medicine to first do a frequentist hypothesis test of the hypothesis that sigma was 0, and then decide whether to fit a fixed effects or random effects model based on how that test came out. And that turns out actually to be a really horrible way to analyze the data. That's called, in economics, it used to be called a testimator, because you actually run a test first to decide which estimator to use. And that turns out to be a very bad way to analyze the data when compared with the answers you get from hierarchical modeling. So people, thank goodness, don't do that anymore. We saw also that an interesting and cool thing called shrinkage comes out of this model. If we pretend that we know what mu and sigma squared are, then the distribution of the theta i's given the data and the mu and the sigma squareds has an extremely revealing form. It's another normal distribution, except it's centered at not at theta I, obviously, because that's a thing we don't know, but it's centered at something called theta I star in this terminology here, and it has a variance given by bi times 1 minus bi. And the theta I star has a really interesting form. If you look at it, it's a weighted average of the data from study I and the overall mean across all the studies. And the weights are given, the amount of weight that's given to the overall mean, b sub I, is called the shrinkage factor, and it represents how far we should take the local answer from study I and move it or shrink it toward the grand mean. And the shrinkage factor has a simple formula. It represents the within study variability divided by the total variability, which is the within variability plus the between variability. And we saw last time that, again, that has a natural expression. If there is little or no between study heterogeneity, then the BIs are all going to be equal to what? Close to what? If sigma squared is close to 0, the BIs are going to be close to 1, and we're going to shrink everything to the grand mean, and that's the fixed effects model again. On the other hand, if the sigma squareds are really big, the BIs are going to be small, close to 0, and we're going to stick largely with the local information. In fact, I can tell you a little anecdote that motivates this whole thing pretty nicely. Let's say that you were measuring mortality rates for a particular disease across a bunch of hospitals. So let me return now to over here and see if we've had any success in getting this thing not to... Okay, we'll work on it in the next break. Anyway, that's actually a little bit better. So this is page 3. And I want to see if it's actually in the frame or not. So let me give it its little framing, guys. So what I'm going to do is I'm going to take a random sample of a bunch of hospitals, capital I hospitals, and I'm going to measure the observed mortality rate for a particular disease. We could think of heart attack, for example, mortality rate for, e.g., heart attack. And I'll call the observed mortality rate at hospital I PI hat, for example, for heart attack at hospital I. Suppose I have one particular hospital where there aren't very many heart attack patients. And so at hospital 6, for example, the sample size at that hospital turns out to be only 10 patients. And the observed mortality rate at that hospital for heart attack patients turns out to be 60%. The overall mortality rate across all the hospitals is a number more like, we could call it mu hat, a number more like 18%, for instance. So now I ask you to play a guessing game with me or a prediction game. I ask you to predict what the observed mortality rate will be at hospital 6 next year in such a way that I'm going to give you more money the closer your prediction is to what actually happens. Here are some possible guesses that you could make. Here's the whole number line from 0 to 100%, and I'll locate 60%, and I'll locate 18%. So here's some possible guesses. You could guess that the mortality rate next year would be above 60%, or you could guess it would be right about 60%, or you could guess it would be between 18% and 60%, or you could guess it would be 18%, or you could guess it would be below 18%. what would you think is best? Is there any reason based on the data you have in front of you to guess a number bigger than 60%? That seems ludicrous, right? Because already 60% is shockingly high at this hospital relative to everybody else. And so this is a pretty stupid guess. Pardon?
Unless there's an angel of death.
Yeah, unless there's an angel of death there, and then we have to, the main way you find angels of death in studies like this is if the person hangs around for a while and that thing persists. Okay, what about below 18%? Is that a good thing to guess? That seems also ludicrous. If we got 60% this time, and you didn't know about shrinkage and random effects and so on, and the idea of pooling information across hospitals, then 60% this year would be a good reason to guess 60% next year. But because, because we know everybody else is getting a rate much smaller than that, and because at the moment we have no reason, like an angel of death or other covariates, to explain why that number came out 60%, wouldn't it be more sensible to make a guess that was somewhere between 18% and 60%? And in fact, what would be your basic reason for why they got 60%? Because the sample size at that hospital was so small. And they just happened to get, it doesn't take much, right? 6 out of 10. We're not talking about 600 out of 1,000. We're talking about 6 out of 10 here. And so the natural thing to do is to shrink their local estimate, 60%, back toward the global estimate, 18%. And the amount of shrinkage we should do should depend upon what? Should it depend upon the sample size at that hospital? Certainly. The smaller the sample size at that hospital, the larger or smaller shrinkage we should have back toward the grand mean. The smaller the sample size at that hospital, the larger shrinkage we should have back toward the grand mean. And also, if I was comparing this with another hospital where things were even more extreme, maybe 75% on a sample of n sub hospital 9, for example, equals only 4 patients, for instance, should I take the 60% and shrink it more back toward the 18%, or should I take the 75% and shrink it more back toward the 18%? The latter, the 75%. So the two things that determine what you should do is how much data there is locally at that one point, at one hospital, and how extreme it is relative to the overall average. The farther away it is from the middle, the more you should shrink it back, and the less data there is at that hospital, the more you should shrink it back. Really important idea. No one even thought about this until the 1950s.
In this problem, isn't it the n? And that determines what your guess should be?
You are actually going to play a game in which you have to sit down now and make predictions for all the hospitals based upon what you see this year. Make predictions next year. And we will construct a scoring rule in which we'll compare your predictions with the actual values. And the scoring rule will have the property that you get paid more money the closer your predictions are to the truth. Under that regime, the best thing to do is not to guess the local number at all. It's to suppose, because we only had 10 patients this year, your implicit supposition is they're probably going to have another small sample size next year, and that this was just a fluke based on small samples, and that it's very likely that next year things are going to be closer to the middle.
Yeah, but so I'm going to assume that my percentages, I got my percentages this year. Really, what I'm trying to figure out for next year is what the different ends of hospitals are, and then use the
Actually, unfortunately, it's not just that. You are simultaneously trying to guess at what the N is next year and what the actual P is for next year. And our best guess for the P next year is that it's some number smaller than 60% and the right amount to shrink. The way to do this that gains you the most money based upon this betting story I'm talking about with scoring how good your predictions are turns out to correspond almost exactly to this shrinkage story that we have in the file. Here's another example of the same phenomenon. Let's talk about test-retest situations. So some of you may have a kid who's taken the SAT or the GRE, for example. So let's take somebody who's taken the SAT, and this is SAT first try. And this is, imagine the same person of a month or so later taking the SAT again, second try. if we make a scatter plot of how these two variables are related to each other across a whole bunch of people, and nobody in the people whose data we got actually went out and did something like got another one, went to one of those schools to learn how to take the test better. And so the only reason that we're getting different numbers each time is just measurement error, essentially, because the tests actually are a little noisy. If you've ever taken one of them yourself, you, for instance, have a good understanding of some words from a vocabulary point of view. What do they mean? What do they not mean? And so on. And which vocabulary words happen to land on your SAT test looks like measurement error to you, right? And if you've take the test again, maybe it'll turn out that you get a different set of vocabulary words. And so your basic knowledge hasn't changed any. It's just that you got different words this time. So what you would find is that under this condition, you'd get a scatter plot that was organized around the line y equals x. This is x, this is y, this is y equals x. So look at the picture. Here's somebody who did really well the first time. What does the story say about what they're likely to do next time? Well, what's that?
They're not going to take it again.
And I'm about to show you why they shouldn't take it. I'm about to show you why they shouldn't take it again. Because if I were to try to use this regression relationship, the correlation regression relationship, to predict what their SAT score would be the second time, the right thing to do actually is to draw a little vertical strip around that point right there, and to say to yourself, well, my best prediction for what will happen the second time is the mean of the y values in that vertical strip for all the people who are similar to this person on the first occasion. And where does the mean fall in relation to that line there? Is it above it or right on that line or below it? Look at it, it's below it. At the other extreme, if you did really poorly the first time, then you're going to find that your prediction is higher than that. And so we do not predict that someone who did really well the first time will do equally well the second time in a situation like this. We predict they're going to do a little less well. And people who do really badly the first time, we predict they're going to do a little better. And this is called the regression effect. What's happening is that this word was invented by a man named Sir Francis Galton around the year 1890. And Galton was a highly aristocratic guy. He actually noticed this first in a data set where we have, they were trying to understand the genetic relationship between height of father and height of son in families. They were trying to understand how height was inheritable in humans. And so they got a random sample of people, or at least a haphazard looked like random sample of families, and chose the father's height, and they picked one son at random in the family and looked at the son's height. And in fact, the father's height and son's height has a correlation that looks rather like this. And if you subtract out the secular trend, because back in the time he did this, each generation was getting a little taller than the generation before it. For what reason would you suppose? Better nutrition, actually. And so the same thing's happening these days. Do you know what the average height of Dutch men is? It's right around 6 feet. Maybe it's 6 feet and a half inch right now. The average height of American men is 5'9", something like that. The Dutch men are 3 inches taller than American men on average. And it's all about diet during the period from being 0 years old to being about 15 or 16 years old. Americans have a completely crap diet throughout their entire childhood, at least on average. And the result is that all of us have a genetically possible height that we were born with, and we fall dramatically short of that genetically possible height because of our nutrition. And the Dutch do a much better job of achieving their genetically possible height. Anyway, if you subtract out that so-called secular trend, he got a picture quite a lot like this. And what he noticed was the tall fathers tend to have what? Tall sons? On average, at least. Tall fathers tend to have tall sons, but look, not as tall as the father was. Short fathers tend to have short sons, but again, not as short as the father was. And it looked to him as though everything was moving back toward the middle, or regressing toward mediocrity was his phrase for it. It looked as though everybody was all of a sudden trying to become just a muddle in the middle rather than being unusual at either extreme. And so he called this the regression effect, and he called the line that you get by connecting together. Imagine now putting all these little vertical strips in there and do the average thing across all of them. You'll get a bunch of points that don't perfectly fall on a line, but if you smooth those points out, you get a line that has a slope that's shallower than this line right here. And he called that the regression line. So what's going on here from a shrinkage point of view? Well, if we look at the distribution of SAT scores, it's going to follow a normal curve pretty well, unless you've got really, really sharp people who are banging up against the top. You can't get more than 800 in some categories. So this is the distribution of SAT scores. And let's say we have somebody who did really well the first time. We know that that number is subject to measurement error. And so the true score for that person is probably somewhere in a little band around there. Now, I give you an option. Is it more likely, looking at the height of the normal curve at this end of things and the height of the normal curve at this end of things, to get that number there the first time, is it more likely that the person actually was even better than the person appeared but got unlucky on the low side the first time? Or is it more likely that the person actually is a little worse than that and actually got lucky on the high side? Check out the heights of the normal curves. Which one of those is more likely? The one over on the left, the explanation that this person actually has a true score that's lower and the person just got a little lucky on the high side. So what happens is that your first score gets shrunken toward the mean in the process of doing a test-retest. And so that's another way to think about this idea of shrinkage. It comes about anytime you do a test-retest in a setting where the summary numbers on the X, the test, and the summary numbers on the retest tend to be about the same. When that's true, and there's a pretty strong correlation between them because it's a test-retest, then you're going to get this shrinkage thing happening. Okay, so let's return now to the PDF narrative. So there's the shrinkage story, and last time we looked at maximum likelihood empirical Bayes. We got an algorithm that was based upon iterative reweighting of the data, and I mentioned that the algorithm can sometimes embarrassingly, to get the maximum likelihood estimates, it can sometimes embarrassingly converge to a negative estimate of the between study heterogeneity, the between study variance. And so you try to avoid embarrassment in that setting by setting that parameter to 0 rather than a negative variance, which is not a very nice thing to try to report to a client, I think you'd agree. These things are called empirical Bayes estimates of the study level effects because it turns out that this essentially approximates a full Bayes analysis in a way that involves using the data to estimate the prior. And that's going to turn out to underestimate variability, underestimate your uncertainty, of course, because you use the data twice, both in the actual likelihood function and also in the prior. And so without adjustment for that, you're going to end up with uncertainty bands that are narrower than they really should be. And there are some adjustments that you can make, but I'm not going to focus on here because we're going to do a full Bayes analysis. So I showed you a little R function that does the so-called maximum likelihood empirical Bayes estimation. We ran it on the data from the aspirin study, and we got an estimated effect of aspirin of an improvement for people's death rate of about 1.45 percentage points, with a rather large standard error in the frequentist world because we have so much between study heterogeneity. In fact, the between study variance with maximum likelihood empirical Bayes was estimated at about 1.53 percentage points squared. And if we take the square root of that, we get a number on the order of about 1.2, maybe 1.2, yeah, about 1.2, maybe 1.23. So there's more than 1 percentage point of heterogeneity between the studies that's unexplained by the data that we have. And we have to describe that at least in order to get a good sense of what's going on in the data and not pretend that it's not there. So I showed you this little shrinkage diagram that shows how everything's being shrunken back toward the grand mean. And we interpreted the maximum likelihood estimates in a Bayesian fashion and worked out that approximate Bayesian posterior, that the posterior probability that aspirin in the population of everybody that we wish to generalize to actually serves to reduce mortality, given the data and relatively diffuse prior information, turns out to be about 96%. And so therefore, I believe all of us would agree that that's pretty strong evidence that taking an aspirin, one of these low-dose aspirins, is in fact a good thing to do. Now, I have forgotten whether we actually ran WinBugs last time. I do recall that I talked you through about how to use Adam and Eve, how to use the two parts of the double expectation theorem to work out what the likelihood function actually is. And I waved my hands for those of you who are interested in trying to work out the full conditionals. I think I ran the R code and showed you what the results were. And maybe, I can't remember whether we actually ran WinBugs on this problem. But what I think we did is I think we ran WinBugs with one particular prior distribution, and we found that it created an anomaly. So here's what we saw when I ran things on and using my own homegrown Gibbs sampler in R. The posterior distribution for sigma with a particular prior, I was using one of those gamma epsilon epsilon priors, which people try to use to express not much information about a variance parameter. And in fact, in this problem, it has the unpleasant effect of distorting the posterior distribution near zero, because in fact, the likelihood function does have significant mass near zero, and so the gamma epsilon epsilon prior, which unfortunately has a big old hairy spike right at zero, is regrettably producing much stronger influence on the posterior than I would have wanted if my goal was to try to have a prior distribution that was diffuse. The gamma epsilon epsilon prior looks like that, and so there's zero, and this is a gamma epsilon epsilon prior, or for instance for a precision parameter, or equivalently something like it for a variance parameter. And what's going to happen is that if the likelihood function does actually have a fair amount of mass right near zero, then the prior is, without us meaning to, it's going to actually have quite a large effect on the posterior, which is not what we wanted. We wanted the prior to not bring in much information. So I think I got as far as showing you what happens in WinBugs with the wrong prior, and then I was about to show you what happens with the right prior. So let's go back into WinBugs again and see how that goes. What do I have open here? I don't need that. Over here, I do need that to be saved, and then get out. Yes, thank you. Fortunately, I hadn't done anything important yet. Let's get WinBugs again, and let's go back to the course web page and grab the files that we need. This is down in the aspirin meta-analysis. So earlier I showed you the R code for doing the maximum likelihood empirical Bayes and the R code for doing the Gibbs sampling, having worked out the full conditionals myself by hand. And now we have the very first aspirin model. Now we can show how to make things better on the fly. So I'm going to bring that in. Chris showed me during the break how to fix that problem of my having always to change the font from 8 point to what I wanted. You can go in, what was it, under Edit, you can choose Preferences, and under Preferences you can hit Default Font, and then over here it was previously 8 and I changed it to 12 and hit OK, and then OK again, and now when I open up the window here and paste it in, it should be what I want. So that's good. That's a little bit of help. Then I'm going to go ahead and get another window, go back to the web page and grab the data. And then I'll do the same thing with the initial values file. So there's the data. Here's the initial values, in which I decided to start things at the maximum likelihood empirical Bayes estimates, because that would be a good place to start in your Markov chain. Okay, nothing wrong with the, well, we will have to change the initial values file in a minute, but nothing wrong with the data set, obviously. But what I want to do now is to put down a better prior, one that turns out to produce better calibrated results. And so instead of putting a gamma prior on the precision, a better thing to do, it's been shown by people like myself and Andrew Gelman and so on, that a better prior is to put a uniform prior on the between study standard deviation parameter sigma. So let's call that, we call that parameter sigma dot theta. And let's put a uniform prior on that. and I'm going to let it be uniform from 0 up to a value that's big enough so that it doesn't truncate the likelihood function. Let's try from 0 out to about 5.0 on the percentage point scale and see what happens. Now, if I try to run this model right here in WinBugs, what do you think is going to happen? Anybody hazard a guess? I haven't told it about the link between tau.theta and sigma.theta, except I have down here, I've said sigma.theta was 1 over the square root of tau.theta. So I told it about the link. But look, WinBugs is going to get confused now, and you would too, because up here I'm telling it sigma.theta is a stochastic node, and down here I'm telling it it's a deterministic node. And so it will certainly not allow that. In fact, I can show you what happens if you try it. Go ahead and try to hit check model. And it says, that's funny. Why would it say model is syntactically correct? That astounds me.
It is syntactically correct.
Oh, okay. Maybe that's what happens. The new model will replace the old one. Now we bring in the data and compile it. Yes, good. And at the compilation stage, it says multiple definitions of node sigma.theta. Okay, good. So you're right. It was syntactically correct. It was just stupid. That's right. Okay. So what do I do to fix that? What do I do to fix that? Do I change the prior line that's stochastic, or the deterministic line down here? Got to change the bottom line now, right? And so what we want to do is we want it to link tau.theta deterministically to sigma.theta and not the other way around. So I go tau.theta is defined to be 1.0 over product of sigma.theta times itself.
How do I use the uniform? You chose 5.
Yes.
And I'm not really supposed to look at the data before.
Oh no, it's perfectly okay to use the data to help you figure out what that should be in the following technical sense. It's not actually using the data twice. All we want to do is to find a number that's big enough so it doesn't chop off the likelihood function. So let me deliberately try to put a number that's too small. I'm going to put in 1.0 and I'll show you what happens. So now does it look like the model is both syntactically correct and sensible? We now have tau.theta defined deterministically in relation to the stochastic node sigma.theta, and that looks like it should work now. So let's have a go. So now I will get myself a model specification tool. Oh, you're right. Good point. And now that I've changed what's stochastic in the prior, I have to change the initial values file. And in fact, let me show you what happens if I don't. You get another error message, which you can figure out pretty readily. You go check model, it's fine. Load data, compile, everything is fine. But now when you go to load the initial values, WinBugs says, it puts the little marker there next, the closest to the tau.theta, and says this initial value does not correspond to a stochastic node. So it works out just what this gentleman here said, that we shouldn't be initializing tau.theta. We should instead be initializing sigma.theta. And so let's initialize sigma.theta to a value rather like we saw in the empirical Bayes story 1.2, for example. Pardon? Oh, you're right. Yeah, that's going to be a syntax error. Thank you. So there we go. So let's try again. Check the model. Yes, I want the new model to replace the old one. Go ahead and Go ahead and now load the data. Data loaded. Compile. Now bring in the inits. Now it just says that mild thing. This contains uninitialized variables, namely all the random effects of theta. So I'll hit gen inits to do that. So everybody's great. Oh, interesting. Look, value of uniform sigma.theta must be less than upper bound. So I tried to tell it to start at 1.2 when actually it only had a prior that went to 1.0. So just for illustration purposes, I'll start it at 0.6. And now everything should be happy. Let me go back and do everything one more time. When you do this yourself, this is the kind of thing that will happen over and over again, right? I'm supposed to try to make it look really smooth up here, but today I'm not doing such a good job of that. Partially on purpose. I hope you'll allow me to look as though I'm doing this on purpose. Now, finally, it gives me this nice message. This chain contains uninitialized variables, and I generate them, and everything's fine. Model initialized. That's what I want. Now let's go ahead and update. And I'll do a burn-in of kind of a ritual burn-in of 1,000, which was probably not necessary. And now let's monitor mu and sigma dot theta, theta, and let's monitor all the thetas. And I don't care about tau dot theta, it's just a technical parameter, but let's definitely monitor positive dot effect. I think I explained this to you last time. Step is a function that gives back a 1 when the thing inside is greater than 0 and 0 otherwise. And so if I monitor this thing called step of mu, that'll work out automatically. I'll get a bunch of 1s and 0s that are 1 every time that mu was positive and 0 every time it was not. And averaging those will give me an estimate of the posterior probability that aspirin is beneficial. So that's a nice thing to put in the model. And so I'm going to go ahead and set that parameter as well. And let's get ourselves the usual 100,000 observations with a refresh of 1,000 and see how that goes. And it just flashes through this quickly like you know what through a goose. And that's because it only has essentially 6 data points to work with, because we are working with actual study level summaries. And now we can look at the posterior. So I will pick out the one I care about the most, which is sigma dot theta, and show you what happened. So having chosen the prior to be uniform from 0 to 1, the posterior looks like that. And right away I say to myself, I have not done what I wanted to. I've chosen an upper bound for the uniform that artificially truncates the likelihood function. So this is the diagnostic for that, and you can go back and make it bigger. So now I'm going to set it to something more like 5. And I'm doing that because you remember the maximum likelihood empirical Bayes estimate for sigma was about 1.2 or so. And I'm guessing that the uncertainty band around that is somewhere a bit less than 1. So probably the values are going to come out somewhere between 0 and about 3 or so. But let's run out to 5 just to be safe. And now I'll start it at 1.2, which is where I really wanted to start it. So go back and kill this guy off and kill that guy off and go back again. What we're doing is the usual thing. We're modeling and remodeling. In this case here, we're remodeling just to make sure that we don't truncate the likelihood function without meaning to. Later on, when we get into model specification, I'll show you a way to both model and remodel in a way that allows you to pay the right price for having gone around around and around the circle doing that modeling and remodeling. So now we've got everything working. I'll go ahead and do my update again. Now I have to do the same monitoring as before, but that won't take too long as I can type without making too many typing mistakes. This time I'll ask for 100,000 updates refreshing every 10,000, and you'll see that'll go pretty quickly also. Wow, okay. So now let's look at the posterior on sigma dot theta. Now it's looking better. In fact, I still see a little bit of truncation. Do you as well? Yeah. It was trying to express itself a little bit to the right of there, and I didn't allow it to do that. So probably it would be better to go back once again and make this a little bit bigger. Let's put it out at 10 and see what happens, for example. Whoa. Thank you, Mr. Bill Gates. There we are. Actually, let's use a value like 6. I think 6 is probably going to be big enough. One more time.
Put the data and recompile.
You have to do everything all over again. If we were in RJAGs, would probably this ring around the rosy thing could have been faster, but here we are in WinBugs, which is okay too. So last time. Okay, now I think it's pretty well tailing off. You might think you would need to go out a little bit more, but I want to show you the results now. There probably isn't that much need to go any farther. So we believe that the between study heterogeneity is substantially larger than what we got by by using maximum likelihood empirical Bayes, and that's because MLEB tends to understate how much uncertainty you have. This is one moment where I wish I didn't have the default font size at 12, because what happens when you do that is that the number that Winbugs prints for Monte Carlo error starts to bleed into the number that it's telling you for 2.5%. So I do have to do a little resizing here. It's better to bring that down to 10 points so that they don't get in each other's way. Well, I think actually that the between study heterogeneity is about 1.9 percentage points of mortality, give or take about 1 percentage point of mortality. And the thing we care about the most is mu, and its posterior density looks like that. Does that look like a normal distribution to you, or a little bit heavier tails than a normal? What do you guys think? I think it has heavier tails than a normal. That's what it's trying to say by going all the way out to, across the 100,000 iterations, it went all the way out to about -7 and all the way out to about +10 in the extremes. So that's a little bit heavier tailed than the normal, and that's because that posterior is behaving quite a lot like T on 5 degrees of freedom, where 5 is one fewer than the number of studies. And so T on 5 has a definitely heavier tail. So we think on the basis of this model that aspirin is beneficial to the tune of about 1.5 percentage points, but we actually have quite a lot of uncertainty because of that between study heterogeneity. And in fact, when I now do the positive dot effect variable, there's no point in plotting the density because it'll just be a bunch of ones and zeros, right? So that's not very interesting. But the summary says that we estimate on the basis of this model that the posterior probability that in the population of people we're trying to generalize to, aspirin has a beneficial effect on mortality is about 93%. That's a bit lower than the number from maximum likelihood empirical Bayes, and that's again a reflection of the fact that MLEB has understated your uncertainty, and so you were trying to make a more definitive statement with maximum likelihood than was actually warranted on the basis of the data. So I actually regard this as quite a good scientific summary of what we have learned from the aspirin data, and if you used the result of this study to predict what a larger meta-analysis 10 years later than this one here would have shown about meta-analysis, as a meta-analysis about aspirin, in fact, this number 1.5 is quite close to the right answer. With more studies, the uncertainty band would get smaller and the posterior probability would get substantially larger, but on the basis of these 6 studies, it was already clear that Amos was some kind of mistake somehow, and that the right thing to do is to give low-dose aspirins to people with heart attacks. So any comments or questions about this one before we go on to the next case study? Yes, and to my knowledge, to this day, no one has ever been able to figure out what went wrong with the Amos study. It seems to me that the most obvious culprit is that there was something systematically different about how they gathered their patients before randomization. Because you know, in randomized controlled trials, yes, you do randomize people to treatment and control, and that tends to balance all the potential confounding factors in the people you're working with. But if you don't do a really good job of getting the people who are about to be randomized in a way that's representative of the population you're interested in, then you end up with a biased answer. And so I think there was something about the way they recruited their roughly 5,000 patients that was biased in relation to everybody with a heart attack. And of course, they weren't very happy they weren't very willing to admit that in print. They got a nice JAMA paper, Journal of the American Medical Association paper out of it that Chris and I were just looking at over the break. So this is the paper on which Amos was based. It was from JAMA back in around 1980, I guess. And right there, you can see it. They're claiming that based on Amos results, aspirin is not recommended for routine use in patients who have survived an MI. And they're giving exactly the same number of people that we have here and exactly the results because we got the meta-analysis data from here. So anyway, that's the story for that. And I think I'll go on to the next case study with your permission. Sound okay? Permission granted. Excellent. All right. So let's get rid of those two and go back to the PDF. Here in the PDF about hierarchical and mixture modeling. Now I'm going to zip through this down to actually sort of estimate. So what you'll see when you go beyond where I was last time is that after these details, there's a WinBugs analysis in which I first try the gamma epsilon epsilon prior and decide that that produces a posterior distribution that's not sensible. In fact, what you see on page on page 25 of the PDF is you get a posterior for sigma dot theta that has exactly the thing I showed you with the Gibbs sampling in R. It has this very unpleasant weird spike at 0 followed by a continuous story heading out beyond 0. That's a big diagnostic that the gamma epsilon epsilon prior was a bad idea. I remind you about that formula about the working out the Monte Carlo standard error. And I try over again with a better prior distribution, and I get answers that are just like the ones I showed you before. Actually, there was one thing I should have shown you. I should have shown you what the story was on the thetas. They were quantities in that model that I wish I had shown you. But let's look here in the static output. I've got some stuff about them as well. So since theta is a vector, when you ask to summarize it in WinBugs, it will give you not just one density, but all of them. So you get to see what the marginal posteriors for all the thetas look like. Some of them look rather normal. Some of them actually look strangely, sharply peaked around a particular value, and they have the following values. We can now compare these things here, this 2.106 and the 2.056 and so on. We can compare those with the numbers we got from maximum likelihood empirical Bayes. And what we find that the Bayesian estimates, first of all, exhibit rather less shrinkage than the maximum likelihood estimates do. And that's because they have 30 to 40% larger uncertainty bands around them. And again, that reflects an understatement of uncertainty on the part of the MLEB story. So looking at the shrinkage plot or the raw data values themselves, as we've agreed, it's evident that a Gaussian model for the thetas may not be appropriate because we have this heavy tail kind of thing. And so what I did was I rewrote the model to have the thetas be draws, IID draws from a T distribution with unknown degrees of freedom, and I put a uniform prior on the degrees of freedom. And in fact, this case I ran one that was uniform from 3 out to 30. And check out the results. On the top of page 32 is the posterior distribution on the degrees of freedom. The prior was uniform from 3 to 32. What's the posterior look like? It's the upper right-hand plot in this picture at the top of page 33. I'm sorry, I got you on the wrong page. So that's the posterior distribution for the degrees of freedom. The prior was uniform from 3 to 32. The posterior is uniform from 3 to 32. And so the data is trying to say to us that this is one of those non-structural, non-identifiability issues. There's no reason in terms of structural defects with the model that parameter should not be learnable from the data. But what we're learning from the Bayesian modeling is that with only 6 studies to work with, it simply cannot figure out what the degrees of freedom should be. And there's an interesting reason for that, which I can share with you here. When you have data that are drawn in an IID fashion from the T model, so if yi is given mu, sigma squared, and nu are IID from T on nu degrees of freedom, but with a location parameter mu and a scale parameter of sigma squared, it turns out that in repeated sampling, the variance of the y sub i's goes like this. It goes like sigma squared times nu over nu minus 2. So suppose I showed you that the data set had a big variance. And you tell from that has to be because the degrees of freedom are, how do you get a big variance? How do you get a big number out of nu over nu minus 2? You make nu rather small, right? Because then the denominator starts getting pretty small and that becomes quite big. So suppose I told you the data had a big variance. Can you conclude automatically and correctly from that that that's because the degrees of freedom parameter is big? I'm sorry, small. It could be either because the degrees of freedom parameter nu is small, or the degrees of the standard deviation parameter is big, right? Similarly, going the other way around, if I find that I have a small variance, that could be either because the degrees of freedom parameter is big or the standard deviation is small. And so what we're learning here is that with only 6 studies, I running from 1 to 6, just the pure fact that the standard deviation of the y's is large does not indicate that we have a lot of information about the degrees of freedom, because we could either get that result from having small degrees of freedom or else large standard deviation. That's why it's so hard to learn the degrees of freedom parameter in the T model with a small number of observations, because there's confounding between the scale parameter sigma and the degrees of freedom parameter nu. Returning now to the PDF. I think we're done with that particular study. So let's go on to the next one. This is from the field of education, and it's going to be an example of a meta-analysis in which we can incorporate covariates. I don't want to overstay my welcome about time for break, but it looks like, yes, it's time for a break. So let's start again. It's 11:20 now. Let's start again right at 11:30. So I am now on page 34 of the lecture notes, part 4, and we're ready to think about our next meta-analysis. And this one is different from the previous one in that we actually do have a study level covariate. So I mentioned to you back when we were talking about the aspirin example that we wished in this Gaussian hierarchical model on page 4, we wished that we had study level covariates, because that would help us to explain why it is that the theta i's were different from one study to another. And if we had them, that would serve to diminish the sigma squared, the between study heterogeneity that's unexplained. And our goal ideally would be to end up with a situation where there wasn't any sigma squared, because we had enough covariates at the study level to actually explain why the thetas are different from each other. In this new case study, we won't have enough covariates to do that, but at least I'm going to show you what happens when you do have a covariate at the study level. So, once again, page 34 of the notes. The question that the people were trying to answer, the educational question, was the following. Do the expectations that teachers have about their students actually end up influencing the students' apparent intellectual development as measured by things like IQ scores and scores on standardized tests? In other words, if you as a teacher expected the person sitting in the second row right on the aisle to do really well, then would it turn out that that person actually did better just because you expected that? There's reason to suspect there might be such an effect, because what teachers will do for people who they expect good big things of is either consciously or unconsciously lavish extra attention on them, give them extra material that will help them enrich the experience and so on. And that's okay for the kids that the teacher thinks are good, but what about the kids that the teacher thinks are bad? That will have a reinforcing effect and make the bad students look even worse, at the same time as making the good students look even better. And that's not necessarily at all what you want in an educational system. In fact, the basic tenets of education, apart from ideas like tracking, where you have a whole classroom filled with people who are in the right tail of the distribution, is to take all the people in your classroom and try to meet them where they are and help them move forward. And essentially offer the same amount of effort on your part for each person, not expecting the same outcome, the same improvement for each person, but at least you find out where the person is when they start, and you try to move each person forward by an amount that's commensurate with the effort you give to each person, which is supposed to be roughly the same across everybody to avoid disadvantage, putting some kids at a disadvantage. So back in the early 90s, these guys, Breik and Raudenbush, who are big guys in the education world, they did a meta-analysis, And this is an important enough topic that even by 1992, there were already 19 different experiments that had all been done to estimate the effects of teacher expectancy on pupil IQ. So we have a table with 19 rows, one for each study. And the estimated effect size, that's going to be our outcome variable yi, like we had before. And the standard error is going to be computed in the same way as before in terms of a frequentist calculation. I need to tell you what an effect size is, and I need to explain this weeks of prior contact variable. So an effect size, we've got a treatment group in each experiment and a control group. And an effect size is measured by the following. It's because the studies did not have the same exact outcome variable, they become difficult to compare until you put them on some sort of standardized outcome scale that's common to all of them. And so a typical thing that's done both in education and meta-analysis and also in medicine and other fields is to take the mean of the treatment group minus the mean of the control group divided by the standard deviation that you get by pooling the standard deviation information from both the treatment and the control. So if you think about it, this is not a question about monies. I'm on page 35 now. It's not a question about money, but if it were about money, TI bar would be in dollars, CI bar would be in dollars, and the standard deviation would also be in dollars, and the dollars would cancel. And so this becomes a pure number without units. And if somebody else were measuring the same income sort of variable in British pound sterling, for example, it would go pounds minus pounds over pounds, and you'd again have a pure number. So that's the idea behind the effect size. Well, did every study get the same effect size, at least approximately, looking at the data? No. They range from a low of minus 0.32, which says that the treatment group actually has worse outcomes than the control group, up to a high of plus 1.18. And so you got some explaining to do about differences across the studies that are as big as that. Those are huge differences on the effect size scale. Well, now I need to tell you what the kicker was in this experiment. The experimental group was made up in every experiment of children for whom teachers were deceptively encouraged to have high expectations. And so here's what the experimenters did. They gave treatment teachers lists of students who allegedly displayed dramatic potential for intellectual growth, but actually the lists of students were generated at random. And the teachers didn't know that. And the controls were students about whom no particular expectations were encouraged. So that was the nature of the randomized controlled trial. So, and this was kids, I think this was kids in grades like third grade, somewhere around there. So the studies ranged in, they varied across something important, namely this thing down at the bottom of this page here. The time period into the term, this was all started in the fall of a new year, and so a new cohort for this third grade teacher. How long was it from the beginning of that term to when the teachers were given this information about Johnny over there is supposed to be a real star, for example? Now, if you're a third grade teacher, your basic model of third grade teachers is that they are caring and perceptive people who quickly form their own judgments about who seem to be the sharp people and the less sharp people in the room. So what effect do you suppose this covariate xi would have? Let's call that xi weeks of prior contact. The bigger that xi was, what do you think we'd have? A bigger or smaller treatment effect? Smaller, right? Because the bigger, all the way up to 3 weeks of prior contact, the teachers who were paying attention would have a lot of information on which to discount this sort of bullshit information they were given about the little lists that were drawn at random, right? And so let's look back. They ranged from 0 to 3 on the covariate scale. This is now a covariate at the study level. And in fact, we start to see that it might actually be helping because look, the 1.18 came from a study where the teacher didn't have any prior contact at all with the kids. And the minus 0.32 came from one where the teacher had 3 weeks of prior contact. So anecdotally, for the biggest and the smallest, we're seeing that it goes in the direction you guys just conjectured. And a very natural thing to do is to make a scatter plot of the effect size as a y variable against the weeks of prior contact as an x variable. And so I did that here. And what I've plotted is there's one circle for each study, but I've chosen to draw things in a way so that your eye is drawn more naturally to the larger studies by making the radii of the circles proportional to the inverse of the variance information in that particular table previously. And so the larger studies are going to have smaller variances, and so basically you want a bigger circle so that your visual impact is larger for the studies that had less uncertainty in them. And I've drawn a weighted regression line of y on x over top of this picture here. Does it look as though there seems to be some systematic tendency for y to go down, the estimated effect size to go down as the weeks of prior contact goes up? Definitely. That line is estimated to be about 0.4 plus 0.4 at 0 and all the way down at about 0.0 at 3. And so 0.4 of a unit on the effect size scale is quite a big difference. And so there's a lot of predictive power.
Most studies were the large,
Let's see. So we have 1, 2, 3, 4, 5, 6, 7, 8 studies with 3 weeks of prior contact. 1, 2, 3, 4, 5 studies with 0. 1, 2, 3 with 1, and 1, 2, only 2 with 3 with 2 rather. So we have actually by accident we have a reasonably good design for the purpose of estimating this regression. If I gave you a chance to design this sort of thing, and I had a designed covariate that was an integer from 0 to 1 to 2 to 3, and I really believed there was linearity going on between the y and the x, and I wanted to get the regression slope as accurately as possible, how should you allocate the experimental units to maximally stabilize your estimate of the slope? You should put half of them at 0 and half of them at 3, right? And so unintentionally, that seems to be what happened. This was not a controlled thing because it was just an observational meta-analysis. These were the studies that were out there in the literature. But actually, they were lucky that we got a lot of 0s and a lot of 3s and not very many 1s and 2s. Now, what's the downside of that in general, though? Suppose you really did the design where you put half of in a designed experiment, you put half the data at 0 and the other half at 3. Then there's no way to judge whether the linearity assumption is right or not. And so no one ever does that design where you put half your eggs in each of those two baskets because there's no diagnostic information about whether the linearity story is any good. You put some points at 1 and some points at 2, not very many, and then you lay the rest, as many as you can, at the 0 and the 3, but just enough in the middle to see whether you've got something quadratic or cubic or weird going on. And that actually, coincidentally, is just about exactly what happened in these particular 19 studies. So it does look like linearity is a pretty good story, and they found that out. Yeah?
So here you gave us the variance to give us an idea of the size. Would it have been better to actually have the actual size?
I don't know how many students there were in each study, but I do know the standard errors of the effect sizes. And so I squared them to get a variance of the effect size, and I took the reciprocal of the variance, which turns out to be the right scale to do weighted things and things like weighted regression. So I tried to draw it so that the studies that had big circles were the ones that had small variability, so we knew a lot about what was going on.
If I was collecting the data by going back to each of those individual studies, I should have tried to get the number of students.
I agree with you. I agree with you. That would be a good thing. In fact, that could be another study level covariate because it won't be perfectly correlated with these V's over here because the V's come partly from the sample sizes and partly from how much internal variability there is in each of the treatment and control groups. All right, so what kind of meta-analysis model would you like to use that now generalizes our previous one by incorporating a study level covariate? Well, you can tell me. Let's look back at the original model and see how we would change it. Is there any reason to mess with the data level of model 1 here, just because we have a covariate at the study level? Well, we're again going to pretend the VIs are known because they were based on fairly large numbers of students. And in fact, the answer to my question is there's no reason to mess with this line of the model at all because by central limit theorem grounds, again, the YIs, which represent the the effect size, estimated effect sizes, should be approximately normally distributed, and each study is allowed to have its own theta. Great. What about at this level, though? This is equivalent to a regression model with only an intercept term, so how should we change it? Write a little regression equation in which theta I is related linearly to what? Xi, right? And you have a normal error term. In the usual way, you'd have a normal error term in a regression model. So let's go down and see what they did. That's just what you should do, and I believe that is what they did. Now, Breck and Raudenbush are frequentists, and so they wrote down a model that, that does not have any priors. But before looking at their model, I do want to make one comment. As we've now seen, evidently model 1, the one we just looked at, where we have only a kind of regression with only an intercept term, evidently model 1 will not do here because it says that your predictive uncertainty about all the thetas in the studies is exchangeable. Whereas we can clearly see from that figure that the xi's are useful in predicting the yi's. And so your uncertainty about the studies is not unconditionally exchangeable, but it becomes conditionally exchangeable given x. In that way, we talked about partial or conditional exchangeability earlier during this course. And so the figure suggests that the y's are related linearly to the x's. This is another example of me cheating with respect to my model uncertainty, right? I looked at the data to decide what form the x and y relationship should have, rather the theta and x relationship should have. And again, starting later today, I think if we get there, and it's certainly occupying us all next week and probably all the next week, we'll be thinking carefully about methods to avoid cheating, or at least either to avoid cheating or else at least pay the right price for having cheated. Those are going to be the two paths we're going to explore. One is there a way to do the modeling that does not involve any of the kind of cheating I just showed you and still gets a good model? And the other way is to say, well, maybe if that doesn't work very well, let's figure out at least how we should pay the right price for cheating. And I'll show you both of those approaches to dealing with model uncertainty. So Breck and Raudenbush were working in the frequentist paradigm, and so they fit the model just like we talked about. The bottom row is exactly the same as before. And now they say, well, theta I, given alpha and beta and sigma squared sub theta, are like independent draws from normal distributions with mean alpha plus beta xi and variance sigma squared theta. And so actually that's exactly the same as a standard regression model, just written in a little bit different way. So for instance, if I chose to write it in the usual regression way, what it would say is, and let me see how many pages we're into so far. It looks like this is page 6. What it would say is that theta I equals alpha plus beta times xi plus ei, where the ei's are assumed to be IID normal 0 with mean 0 and variance sigma squared sub theta. That's exactly the same as saying this is equivalent to saying that theta I given alpha and beta and sigma squared theta, and also given the x's, of course, but we're thinking of the x's as fixed known constants, so we don't even have to condition on them. We're thinking of the x's as fixed known constants, which they are, that the theta i's are like independent draws from normal distributions with mean alpha plus beta xi and variance sigma squared theta. Because look, what's the mean of theta I in this model? This is the first expression of the model. If the ei's are IID normal with mean 0, then the mean of the theta I has to be alpha plus beta xi, just like it says down here. And since this expression here, this involves a kind of a constant added to a normal curve, the overall theta i's also have to be normal, just like it says down here. And adding a constant to something doesn't change its variance. And so the variance of the theta i's has to be the same as the variance of the ei's. So in fact, these are two perfectly equivalent ways to write down the same model. And on the PDF notes, I've chosen to write it in that second way. But it's just like a regression model where the thetas are regressed on the x's. So according to this model, the estimated effect sizes y sub I are like draws from a Gaussian distribution with mean theta I and variance vi, and in fact they're independent draws from Gaussians. And the vi's are just the squared standard errors from that column, the last column of that table I showed you a little bit before. And here, as in our earlier aspirin meta-analysis in Model 1, we're pretending that the VIs are known, and again, there's not much harm in doing that. And then the theta i's themselves are like draws from a Gaussian with mean alpha plus beta xi and variance sigma squared theta. And in effect, what's going on here is, since things are conditionally exchangeable given x, the top level in this model in effect assumes, one way to talk about what it's assuming is that the 5 studies that had x equals 0 are like a representative or random sample from all studies you could have run with x equals 0. So we're generalizing outward to other studies that could have been done of exactly the same treatment with different classrooms involved than the ones they actually used, and similarly for the other values of x. Yes, please.
Can you explain?
Oh, I'm just using that notationally. We could have called it sigma squared like we did before, but here I'm going to call it sigma squared sub theta to emphasize the fact that it's the variance between the thetas after accounting for the mean differences. So I could have just called it sigma squared, and it would have been like the number we had before in Model 1. I just happened to give it this name. So it's not actually, the sigma squared doesn't depend on the value of theta. It's just a notational story. Thanks for asking that. This assumption here about the representative sample from a larger population and the Gaussian choice up here, because we don't know that for sure that things would be Gaussianly behaved, although we can get some sense from looking at that scatter plot about whether the residuals from this regression line would follow. In effect, what we're assuming is that the variability around the true thetas, which should look something like the yi's, should have the property that the amount of vertical scatter in each column, 0, 1, 2, 3, is about the same, which might or might not be true here, and that there's a linear relationship between the two, which does seem to be a pretty good summary of what's going on. But the assumption of the samples we have, the studies we have, as being like a random sample from other studies that could have been run, and the Gaussian assumption are not scientifically forced assumptions. They're just conventional assumptions. For instance, if you know of some way in which 2 of the studies with x equals 3 differ from each other that's relevant to the outcome here, that should be added in as another study level covariate. But in this problem here, we don't have any other study level covariates. We only have the one I've shown you. Now, here's going to be a drawback of maximum likelihood empirical Bayes. Breik and Raudenbush used MLEB methods based on the EM algorithm, which we don't need to talk about here, I don't think. It's a technical way of computing maximum likelihood estimates in random effects models. This is going to be another one of those random effects models, right? Because the thetas are unobserved, and they act like random effects in describing how the y's are different from each other. Unobserved corresponds to the word random in the phrase random effects. And so they use the methods that are similar to the MLEB method I showed you before. And what this does is, in effect, it combines the 2 levels of the model to construct a single likelihood function. So in the jargon, you integrate out the random effects theta I, and you end up with a likelihood function that relates the y's only to these parameters alpha and beta and sigma squared. And then you maximize the likelihood in this empirical Bayes way, where you use the data a little bit to estimate the prior. And when they're done, they obtained the following estimates. So alpha hat came out about 0.407, give or take about 0.087. Beta hat, the slope should have been some negative number, and it was, minus 0.157, and the give or take was rather small. So this slope is not only negative as it should be, but it's also so-called statistically significant because the signal's a lot bigger than the noise. And they ended up, however, with an estimate of the variability between the studies after the covariate had been taken into effect of 0. In other words, the claim from maximum likelihood empirical Bayes is that all of the study level variability has been explained by the covariate x. But the reason for that is something that I think I've sketched for you before. If we were to look at the marginal likelihood function for the sigma squared theta parameter, given the data in this model, we would find that it looks like this. And so if you're a maximizing person, what would you say is your best estimate of sigma squared theta? The maximum occurs at 0. And so here, if you were only maximizing that curve, sigma hat squared theta would have to be 0. But in fact, when thought of as a density in a Bayesian fashion, but Bayesianly, if there's such a word, the entire distribution, if this is an approximation to the posterior distribution for sigma squared theta, given y with a flat prior, but Bayesianly, the entire distribution is to the right of 0. So 0 is maybe not such a good summary of what's going on. And what happens then is if you go ahead and pretend that this sigma hat squared is 0, that will propagate through to your estimates of the uncertainty about the other parameters, the alpha and the beta, and it will make those estimates look more accurate than they really are. The right uncertainty bands should be bigger than the 0.036 here and the 0.087. Oh, sorry, thank you. Good. What happens when you pretend, naively, based upon the maximizing story, that sigma squared theta is 0, is that it's going to turn out that this number here, plus or minus 0.036, is driven in part by sigma hat squared theta, and so is this 0.087. Both of these standard errors include components of variability between the studies, and so these numbers are going to underestimate how much uncertainty you have because you took a likelihood function that was heavily skewed with its maximum at 0 and pretended that was a good summary. So this is not a good way to analyze the data. From a Bayesian point of view, this model is missing a third layer. We need to have a prior distribution on all 3 of those parameters. And actually, you may or may not have ever noticed this before, but in regression, to stabilize the estimation of the parameters alpha and beta, it's a good idea to center the x variable by subtracting off its mean. And I can make a little sketch that shows why that's true. Suppose I had an XY relationship where the point cloud was way over here. And there's the middle of the point cloud as far as X is concerned, X bar. And I'm going to now try to fit a regression line to this, and it's probably going to look something like this. It's going to go through kind of like that, a little bit flatter than the line you would get by going right down the heart of the ellipse. From a stability point of view, if I ask you to put something like my pen here and balance it, make it go right through the line and right there, small changes in the data would cause fluctuations in the slope. And in fact, a small change in the slope would have what kind of change on the intercept? Because the point cloud is so far away from 0, changing the slope by a small amount would have what effect on the estimated intercept? It would magnify it. It would have a bigger effect. And it's like a lever, that's right. And so you notice actually that what you're going to see is that the correlation between the alpha hat and the beta hat in this model is going to be what? Positive or negative? As the slope goes up, the intercept goes down. And so this is going to be less than 0, and it might be quite strong, could be quite strong. In fact, it's going to be quite strong, and it's going to be stronger as X bar does what? Gets farther away from 0, as X bar gets farther from 0. So, a better way to work with the regression, this is the regression line y equals alpha plus beta x plus e. A better way to work with regression from a stability point of view is to subtract off the X bar from the X. And so now the new place now the new scatter plot is centered at 0, and we have the new model y equals alpha star plus beta times x minus x bar plus e. And what happens to the correlation between the alpha star and the beta now? You can move the slope around all you want, and it has no effect at all on the intercept because the intercept is right at the center of the point cloud. And so with this model here, the correlation between alpha hat and beta hat is what? 0. So that's a good trick in regression to stabilize the joint estimation of the parameters by centering all the x values by subtracting off their mean. In fact, it can be useful to do a full standardization where you subtract off the mean of each x and divide by the standard deviation of each x as well, if they're all quantitative. And then the betas all come out on a relatively common scale, because whatever, if x1 was in pounds of weight and x2 was in dollars of money and so on, computing x1 minus x1 bar over sx1 converts it into a pure number, and doing the same thing for x2, a pure number, and now the betas become more comparable to each other. Previously, they had no direct comparability because the units were different. So standardizing your x's before putting them into a regression is a good idea from an all-around perspective. And it turns out in the Bayesian world to be a good idea to do it because it stabilizes the Markov chain Monte Carlo work, the sampling we're about to do with wind bugs. So like it says here at the, below equation 33, it will help convergence of the MCMC to make alpha and beta uncorrelated in the posterior by centering the x's at 0 rather than at x bar, and we do that by subtracting off. We create a new predictor. We could call it x prime, xi prime, which is equal to xi minus x bar. And so, as will subsequently become clear, and in the next few minutes as we do the Bayesian fitting, the trouble with MLEB in a model like this is that in Bayesian language, it assumes in effect that the posterior for sigma squared theta is in fact point mass on the MLE instead of having uncertainty about that value. And this is bad for at least two reasons. As I've shown you with that little sketch with the J-shaped, the reverse J-shaped likelihood function, if the posterior for that sigma squared parameter is highly skewed, the mode will be a poor summary. And secondly, whatever point summary you use, pretending that the posterior standard deviation for that parameter is 0 clearly fails to propagate uncertainty about it. And it turns out that uncertainty in sigma squared theta should propagate correctly in the equations through to uncertainty about alpha and beta and the theta sub i's. And so the best way to carry out a fully Bayesian analysis of this model is with MCMC methods. And so on pages 38 and subsequently, I have a static version with a series of screenshots. Now let's actually do it in real time and see what we get. So once more into the world of wind bugs. Go back to the course webpage and this time grab things from the the teacher expectancy case study. So here's my first teacher model. We're going to do better than this model in a minute, but let's start here. And that's my model. Now I'll go back and grab the data, which again is a fairly small data set. We have 19 studies, so 19 data points. And I get the taus, the precisions for the y, in exactly the way I did before in the aspirin study. Precision is always 1 over variance. That acts like 1 over v, and I got the v's as the squares of the standard errors in that column in the table I showed you. So I just use R to compute those numbers and stick them in this vector called tau. It should really be called tau.y because it represents the uncertainty on the y scale, but okay. Call it what we want as long as we don't get too confused. So there's my data set. And now let's get the initial values and then we're ready to go. Well, I'm about to talk about that. This is one of these default priors for the variability between the studies, and I'm about to show you that that's not a very good choice. So the data set's pretty clear. It has a list structure as usual with a vector of y values, a vector of x values, a vector of those tau values which represent the precisions for the y's, and a notation that n is 19. The initial values file is also pretty straightforward. I simply start the chain off at generic starting values. Since alpha and beta live on the whole real line, I start them off at 0. And I'm about to put a prior on tau.theta rather than sigma.theta, and I just start that generically off at 1 because it lives on the positive part of the real line. So let's talk first about the likelihood, sampling distribution likelihood part of things, and then I'll talk about the prior. There's a function in WinBugs called the mean. And what you do is you put in a vector inside that function, and it'll work out the mean of the vector of numbers. And the way you tell it as a vector is you say x open bracket, close bracket, and that says that's the syntax in WinBugs to express the fact to WinBugs that the x object is a vector without saying what its length is. It'll work that out by other means. In fact, it'll work it out by seeing how long it is over here in the data. And so I create a static node, a deterministic node in the graph that's simply the mean of the x's. And then as I loop through the whole data set as I runs from 1 to n, I create mu sub I, and I do that deterministically by working out alpha plus beta times xi minus x dot bar. And then my model is hierarchical. I say that the theta i's are like normal draws with mean mu sub I and a variance of rather precision of tau dot theta. And then the y's are normal draws centered at theta I and with precisions tau I. And that should, as I said, be tau dot y, probably would be a better name for it. In fact, I can put that in without much trouble. I'll say tau dot y over here and tau dot y over here, and that's sort of a little better notation for what's going on. Now, I want to express the information in this analysis that I don't have much information ahead of time before I saw any of this data. And so I want to use diffuse priors for alpha and beta and some aspect of the variability for the thetas. And I'm going to use the usual normal priors with mean 0 and huge standard deviation or variance equivalent to very small precision. This is like, each of these is like saying alpha and beta in the prior could be anywhere from about minus 3,000 to plus 3,000. And it's going to turn out their values are around 1, something like that. And so, with 19 studies, we have a fair amount of learning going on, and so the likelihood function is going to probably be somewhere right around the point estimates, not too far away, and that means that these priors are going to be close, very close to flat in the region where the likelihoods are appreciable, just like I want. But to show you the effect of this, the state of the art in this kind of hierarchical modeling, as of about the year 2005, was to just go ahead and slap one of these unthinking gamma epsilon priors on the precision. That's what everybody did. But then some work that I did with a student, Bill Brown, and some work that Andrew Gelman did showed people that a better prior was to put like I've shown you in these models, a uniform prior on the standard deviation, running from 0 to some number that is just barely big enough to not truncate the likelihood function. So first I'll show you what happens with this particular prior here, and then I'll go back and show you, then we'll edit that and see how much of a difference it makes. So tau dot theta is a stochastic node in this graph. And I want to monitor sigma dot theta. That's the scale in which I think. And so I'll just tell it it's 1 over the square root of tau dot theta. So that's my model. And now let's see how it goes. So I go ahead and check to see if it's okay. And it's syntactically correct, thank goodness. And I load the data and compile. Everything seems hunky-dory. And I hit load inits. And as usual with random effects, in this case the thetas, they are nodes in the graph that are not yet initialized because I didn't initialize them all over here. So I'll just hit the gen inits button, and that will finish that off. Now everybody's initialized, and the model is ready to go. So I can now, as usual, do an update, burn-in update. And so, as usual, I'll just use this kind of knee-jerk traditional burn-in of 1,000. Probably not necessary, but let's go ahead and do it. And it goes very quickly. Not quite as fast as the aspirin study because we have 19 studies now rather than 6, but still. And now let's go ahead and, let's go ahead and get our monitoring. Have a look. So I wish to monitor alpha and compare the answers with the MLEB answer. I want to monitor beta. And I'm not that interested in tau dot theta, but I do want to monitor sigma dot theta. And I'm also interested in the thetas. So let's go ahead now and get ourselves our generic 100,000 with a refresh every 10,000, and that's going to go pretty quickly. And now let's see what we get. So first of all, you're always going to want to look and see if sigma dot theta looks reasonable. And here we don't have anything really pathological going on. The likelihood for this particular parameter on the sigma theta scale does not have a huge amount of concentration right at 0 or near 0, so we don't have that funny spike that comes from the tau, from the gamma epsilon epsilon prior. But this already does show that we have pretty substantial Bayesian sensation, at least, that the posterior for sigma dot theta, in fact, does not have any kind of enormous concentration right at 0. And therefore, the MLEB idea that that parameter should be set exactly equal to 0 doesn't seem to be well supported by the Bayes analysis, right? So in fact, we think that the mean does turn out to be a pretty small number. It turns out to be about 0.06 with a give or take of about 0.03. So I can understand how the MLEB analysis would get confused. But in fact, it's not the case that all of the variability between the studies has been perfectly captured by the covariate. It's just that most of it has. And so this is a better description of what's going on, and we'll get a better one than that in a minute. According to this model, the alpha comes out with a density that looks like a normal curve pretty much, and parameter values that are behaving like around 0.13 or so, and with a give or take of about 0.04. You look at that alpha in this model here, and you go back to the look at what's going on in here. We found that Breik and Raudenbusch were getting, in this particular model here, model 32, they were getting an alpha on the order of 0.407. Here in the Winbugs, we're getting an alpha that looks like more like only about 0.14. So those numbers are really different, and either that's because of Bayes versus maximum likelihood, or it's something about the model that's different. And check it out. Compare model 33 with model 32 and see if the alpha has the same meaning in both models. So here's model 32. Yeah, of course, the intercept is different because in the case of the Bayesian model, we centered the x by subtracting off its mean. So that's equivalent to the Breik and Raudenbusch model if we wrote it in the form alpha minus beta x bar plus beta times xi, right? Because we had a beta times xi minus x bar. And so naturally, they're quite different from each other because they aren't the same thing. I should have called them different names, right? I should have called this one down here alpha star, and then we wouldn't have been, or some other name, or alpha prime, then we wouldn't have been so tempted to compare them and see. But look, the alpha has a standard error in frequentist language, or a posterior standard deviation of about 0.045. That is directly comparable with that's funny, because, oh no, it's not. You're right. The whole thing is, never mind, the whole thing, because it's on a wholly different scale. So I take that back. These are just different numbers. They can't be compared directly. The beta, though, should be comparable. So let's check out the beta story. So the density, again, looks sort of like a normal curve. And we estimate the slope, the effect of the covariate on the study results, to have a slope of about minus 0.16 with a give or take of about 0.039. And the story from here was about minus 0.16, give or take about 0.36. And so if this were a good prior to use on sigma squared theta, then we would find that these results are in pretty good agreement with each other. And at the end, we could look at all the thetas, for example. And so what happens when you do that is that now you're wishing you did what that gentleman told me to do, kind of move the update tool and the sample monitor tool out of the way. Since there's 19 of them, Winbugs gives you all 19 of their marginal posterior distributions, which mostly look Gaussian, not too far from it. And I can also ask for the stats, and it gives a big old hairy table, all of which I have to make a little smaller so that things don't run into each other. And now on this 10-point thing, they're all kind of, you can look at them all and see what's going on. And I'll have something more to say about those values in a minute. but these represent the shrunken estimates, essentially. What were we doing with the shrinkage story in the previous model? Well, that was page 7, and now we're on page 8. So with model 1, and remember model 1 looked like this. Yi given theta i's were independent normals with mean theta I and variance v sub I. And then we had that the theta i's given mu and sigma squared were IID normal mu sigma squared. And in fact, this mu here is sort of like the alpha because it represents a regression with only an intercept term. And then we put a prior on mu and sigma squared. So they got a prior, got a diffuse prior, so I'll just say that they're diffuse. That's model 1. Now, model, whatever I called it over here when we were working with, I guess it's model 33. The bottom layer is exactly the same. Normal theta I vi. But now, the theta i's given alpha and beta and sigma squared theta, now they are independently normal with mean alpha plus beta xi minus x bar and sigma squared theta, and then I put a diffuse prior on the alpha and the beta and the sigma squared theta. So in model 1, all of the thetas ended up getting shrunken toward what? The grand mean mu. Here, the theta i's get shrunken toward mu. But here something cool happens. What's happening here? Here, the theta i's get shrunken not toward a single number, but toward what? Toward the line, exactly. Toward the line, alpha plus beta xi minus x bar. And so when there aren't any covariates, shrinkage is toward a point. And when there are covariates, a single covariate, you shrink everything toward the line. And if there were more than two or more covariates, you'd be shrinking toward a plane or a hyperplane. So that's how shrinkage works when you've got covariates at the study level. But we should find that all of the theta i's are closer to the line than the y sub i's are. That's a way to think about it. And in fact, that should show up if we were to plot that same scatter plot. I didn't think to do that here. If we look at this scatter plot on page 35, there are the y sub i's. I could plot the point estimates, the posterior means for the theta i's on the same graph with different plotting symbols, like little triangles or something. And you would find that every single triangle is closer to the line than the dot, than the circle that corresponds to it. That's what's going on with shrinkage. So back in the Winbugs world, we have all these guys. And if you want, you could explore how well things are mixing. You could look at the beta parameter and look at its autocorrelation function and see that because of the presence of the random effects, it's not mixing at all well. This is one of the worst ones that we've seen all quarter, all course so far. That looks like an AR1 with a first order autocorrelation of about plus 0.9. That's really not mixing well at all. And yet you may recall that with 100,000 iterations, which only took just a fraction of a second to do, even with that quite bad mixing from a technical MCMC point of view, we've already achieved a Monte Carlo standard error for the mean on the order of 0.0007. So essentially, here it is again. We overcome the Monte Carlo inefficiency of the basic MCMC algorithm, which shows up in this nasty autocorrelation function. We just overcome it by brute force. We hit the whole sampling process with 100,000 draws, which is virtually instantaneous, and we're able to get a really tiny Monte Carlo standard error just because we have so many draws going into the quantity. So returning now to the screenshots, you can see that I showed you much the same story. Now what I'd like to show you is what we get with a better prior on the scale parameter for between study heterogeneity. So this tau thing getting a gamma epsilon epsilon prior was state of the art, at least a kind of careless state of the art as of about 2005. This is still a relatively recent research issue in Bayesian statistics. But as I said, Gelman and I and others have shown that this is not the best prior to use if you're trying to, what do I mean by best? If I'm trying to produce intervals for the other parameters in the model that I care about, and also intervals for sigma dot theta that are well calibrated, in the sense that if I generated a whole bunch of data sets from this basic model and asked how often my 95% intervals included the truth, I get a better calibrated story by putting a uniform prior on sigma dot theta rather than putting a gamma epsilon epsilon prior on tau dot theta. So as we did before, I'm going to now.
That last bit, about 95%.
Yes, in fact, I'll write it down. So uniform 0C prior on sigma theta, better calibrated than gamma epsilon epsilon prior on 1 over sigma theta squared, which is tau theta. And what I mean by that, I can write on the next page. So these are the research results. Actually, I need to write myself a note. There's a paper I want to show you by my student Bill Brown and I, in which Gelman's results are part of the discussion. So let me do that for next time. Put that on the web page. I could probably put it on the web page over lunch, so we'll see. Anyway, what do I mean by that? So the main way that, as a Bayesian, I want to know how well calibrated my Bayesian modeling is by means of the following sort of simulation experiments. So I'm going to conduct a simulation study in which I do the following. Generate many data sets from, and many might be on the order of 1,000 or 10,000 data sets. Data sets from model 33, which is back here, you'll recall this model here. Except since we're in the simulation world, we get to play God. We know what the parameters are because we're the ones who set those values. So this is the only time in your whole life that you actually get to know whether your confidence intervals or your intervals, your inferential intervals include the truth. Apart from that St. Peter thing I told you about a while ago, this is the only time you get to find that out because you yourself are controlling these parameters. So now I'm going to generate many data sets from model 33 with various choices of known vectors of the form alpha, beta, sigma, theta. Those are the parameters in this model. So generate many data sets from model 33 with various choices of known parameters. Construct 95% inferential intervals for alpha, beta, sigma, theta on each data set. I'll put that 95% in quotes. This is what people call the nominal coverage level of these intervals. In other words, we're hoping that 95% intervals that we call so-called 95% intervals will actually include the truth about 95% of the time. That would mean good calibration. So construct 95% nominal inferential intervals for those parameters on each data set and keep score. What is the actual percentage of time these intervals include the known data generating parameter values. Yes, please. And so these things here are, I'm going to call them the data generating, because we are the ones who generate the data from them. These are the data generating values. So now you ask the question, what actual percentage of time these intervals include the known data generating parameter values? This is called the actual coverage rate. This number here is called the actual coverage rate. And if nominal is approximately equal to actual, then you say you have good calibration. That make pretty good sense? Good calibration for that particular way of learning about these parameters from the data. And the main thing that you can vary to see whether you get good calibration or not is you can try putting down different priors, all of them diffuse, on these parameters and see which choice of priors gets you better calibration in this sense. And what my work has shown and Gelman's work has shown is that it doesn't matter very much what you put down for the prior on alpha. It doesn't matter very much what you put down for the prior on beta, but it matters quite a bit for what you put down for the prior on either sigma dot theta or else sigma squared dot theta or else 1 over sigma squared dot theta, which is the precision. And instead of putting a gamma epsilon epsilon prior on the precision tau dot theta, we're going to put a uniform prior, like I showed you in the previous case study, on sigma dot theta. So it's going to be d unif from 0.0 to the kind of value, a value big enough to avoid truncating the posterior from the previous gamma epsilon epsilon prior. So this is a sense in which the gamma epsilon epsilon prior is useful. You can make a round 1 model fit with the gamma epsilon epsilon prior and see what kind of posterior you're getting on sigma, and that will tell you how far out to go in the tail in the uniform 0, comma, blah, blah. That tells you how big to pick the blah, blah in order not to truncate the likelihood function. Here it looks like we can stop it at around 0.2. And what Gelman and I have shown is that what you should do is to try to find the smallest value of C, the cutoff point, uniform 0C, find the smallest value you can that avoids truncating the likelihood function. And it turns out that especially when you have a small number of studies, the upper endpoint of the uniform interval still has more effect on the answer than you would like. And the bigger you make that number C, the wider the uncertainty bands get. And so in order to get answers that are well calibrated, so what will happen is that if you let it be too big, your alleged 95% intervals will include the right answer 98% of the time, for example. Those intervals are wider than they need to be. And so to get just the right amount of calibration, Goldilocks, porridge too cold, porridge too hot, porridge just right, in order to get just the right amount of calibration, the right amount of coverage for nominal 95%, find the value of C that just is the smallest value you can find that just barely fails to truncate the likelihood function in the posterior and your golden. So here I'm going to try 0.2 and see what we get. Okay, good. So, and as before, this model isn't going to fit because I've got multiple definitions of sigma dot theta, so I have to go back down here and deterministically define tau dot theta to be 1 over sigma dot theta squared. And another much less euphonious way to do that, as I've mentioned to you, is you can use the POW function, the power function, on sigma dot theta and raise it to the power 2. And then I have to put in another parenthesis, I guess, to make it be syntactically correct. Have I shown you what happens with syntax errors in the model? That you actually get good diagnostics from WinBugs? What it'll do is it'll beep at you, and it will relocate wherever the cursor was, the blinking cursor. It'll locate it very close to where the mistake was. And so it actually gives you pretty good diagnostic information about what the problem was. So that's going to be my new model, and as we've seen before, that means I have to change the initial values to have them relate to sigma dot theta. But look, if tau dot theta was 1, so is sigma dot theta, so I'll just rename it in the... Ha! Ha ha! Good for you. So I have to use something more like 0.1. Good for you. Spoken like someone who is accustomed to anticipating problems before they exist, before they're found out. So I check the model, and it looks fine. And I read in the data, and compile, and I read in the inits, and gen inits, and I'm up to speed. Now I go back and update, and there's my burn-in. Now I monitor everything I want to. So there's alpha, there's beta, there's sigma dot theta. No, you have to hit the set button. And the thetas, let's look at the thetas again. That's about all I care about. You could monitor the mu's as well if you wanted to, because they are deterministic functions of stochastic nodes, so you could monitor the mu's as well if you wanted to. That would be kind of interesting, perhaps. All right, now let's go. We go ahead and get our big update and refresh every 10,000. It's go by pretty quickly. So 2 seconds for that updating. And now, as usual, let's minimize these guys to get them out of the way. Oops, sorry. And focus in on what we care about. So first of all, let's see how much that changed things for sigma dot theta. The density is now very different looking. Now it looks more like, isn't that interesting? It looks more like the reverse J-shaped distribution that we were getting from the likelihood function that I showed you before. No wonder the MLEB method gives a point estimate of 0. And yet you can show, using simulations of the kind I just showed you how to do, that 0 is a very poor summary of what's going on here, and that you actually get better frequentist answers by using Bayesian fitting. And the whole reason for that is that integrating over the likelihood function instead of maximizing over it is just purely a better frequentist technology when the likelihood function is badly skewed. When it looks like a normal curve, integrating over it and maximizing over it are going to give you what? Same thing, because the mean of a normal curve is at the same place as the mode. But when the likelihood function is nastily non-normal, maximizing over it can well give a deeply inferior summary to integrating over it. And so now we get rather different summary numbers. And also, for the things we care about, let's look at the beta parameter, for example. It has a density with a little bit of raggedness going on around the mode. This is a function largely of the default choice for in WinBugs for how the so-called kernel density estimation should be done. You may or may not have heard recently about how kernel density estimation is done. I think I gave an intuitive hand-wavy sort of description of it last time. What you do is you put something like a running histogram on the data, and you move the little histogram bar from left to right, and you get a little local estimate of how much data is in that little histogram bar, and then you smooth that. And a lot depends upon how wide the histogram bar is. That's called the kernel width, basically. And what I think is happening here is that WinBug's default kernel width is a little bit smaller than it should be, because they end up thinking that there's some interesting structure going on around the mode when in fact it isn't really there. And if I had taken 1 million samples instead of 100,000, that would be nice and smooth. And actually now we seem to be getting answers that are quite a lot like the MLEs as far as the uncertainty band goes. So let's go back and look. Didn't we have values like minus 0.16 or so from minus 0.157, give or take about 0.036. Here we're getting about minus 0.160, give or take about 0.038. So we have a little bit more uncertainty than the MLEB story is showing, but it isn't desperately awful. So the moral here, and it's time for lunch, the moral here is that there is a lot of effect on the posterior distribution about the things you care about in these hierarchical random effects models. There's more effect than you would like in how you specify the diffuse prior on the between study heterogeneity. And the right way to do it based upon current research is to put a uniform prior on the standard deviation scale rather than any other kind of prior on any other scale. You get better calibration doing that. So let's take our lunch break. We'll start again at 1:30.